The universe is older than the universe. That sentence should not make sense. And yet, after 2 years of staring deeper into space than any instrument in human history, the James Webb Space Telescope keeps sending back images that suggest exactly that. Galaxies that should not exist. Black holes too massive for their age. Elements that demand billions of years to forge, glowing in stars that ignited just 300 million years after the Big Bang. Not one anomaly, not two. An entire population of objects sitting in the infant cosmos, like fossils that predate the soil they were buried in. Cosmologists built an elegant model over the last century. 13.8 billion years, a single origin. A universe born from nothing, expanding, cooling, assembling itself one star at a time. It worked beautifully until Webb turned on. Now, some of the most respected minds in physics are saying it out loud. The Big Bang may not have been the beginning. It may have been a transition. Roger Penrose, a Nobel laureate who proved black holes must exist, has spent the last 2 decades developing a theory that most of his colleagues dismissed as mathematically interesting but physically ridiculous. He calls it Conformal Cyclic Cosmology, and it suggests that our universe inherited its structure from a previous one, that the so-called beginning was simply the moment one dying cosmos handed its blueprints to the next. That time does not start, it cycles endlessly, and the James Webb Space Telescope may have just given us the first hard evidence that he was right all along. This is not speculation. This is not fringe science whispered at conferences. This is data, and it is rewriting everything we thought we knew about where we came from. This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. We have been walking around for more than 60 years believing we know when the universe began. 13.8 billion years ago. That number is everywhere. It's in textbooks, museum exhibits, documentaries narrated by people with soothing voices. It sits at the foundation of cosmology like bedrock. The Big Bang Theory, polished and refined through decades of observation, tells a story so widely accepted that questioning it feels almost rude. A hot, dense point, an explosion that wasn't an explosion because there was no space for it to explode into. Rapid expansion, cooling, the first atoms forming in a cosmic fog, then darkness, then light. Then stars, galaxies, planets, you. The story has been told so many times, it has the feeling of scripture. Except there's a problem. The James Webb Space Telescope launched on Christmas Day 2021, and what it found when it opened its infrared eyes on the early universe was not what the story predicted. Not even close. By mid-2022, the first scientific images started arriving, and within months, cosmologists were using words like unsettling, unexpected, and in private conversations, impossible. Because sitting at the edge of the observable universe, in a time when the cosmos was supposed to be filled with nothing but dim clouds of hydrogen and helium gas, slowly clumping together, Webb found galaxies, fully formed galaxies, massive ones. Galaxies with structures that should have taken billions of years to build, sitting there like someone had quietly redecorated the house while the owners were out. Let's start with what we thought we knew, because the cracks only make sense if you understand what was supposed to be holding things together in the first place. The Big Bang model is not a wild guess. It is backed by an extraordinary amount of evidence. The cosmic microwave background, that faint glow of radiation left over from when the universe was only 380,000 years old, matches predictions so precisely that physicists have measured its temperature to within a few millionths of a degree. The abundance of hydrogen and helium in the universe, the redshift of distant galaxies, the way light from the earliest stars gets stretched by the expansion of space itself. All of it fits, the math works, the observations line up. For decades, this framework has survived every test thrown at it. The story it tells goes like this. In the beginning, if you can call it that, the universe was unimaginably hot and dense. Everything that would ever exist, every atom, every photon, every bit of energy in the entire cosmos, compressed into a volume smaller than a single atom. Then it began expanding, not into something. There was no outside. Space itself was stretching, carrying matter and energy along with it. In the first fractions of a second, the universe cooled enough for the fundamental forces to separate. Gravity split off, then the strong nuclear force. The universe was still far too hot for atoms. It was a seething plasma of particles and radiation, opaque to light, like being inside a star. For the next 380,000 years, it stayed that way. Then, as the universe continued expanding and cooling, electrons finally slowed down enough to be captured by protons, forming the first neutral hydrogen atoms. That moment, called recombination, is when the fog lifted. Light could suddenly travel freely through space. That light is still traveling. We see it today as the cosmic microwave background, the oldest light in the universe, a faint radio hiss coming from every direction at once. After recombination came what cosmologists call the Dark Ages. The universe was filled with hydrogen gas, neutral and cold, drifting in vast clouds, no stars yet, no galaxies, just darkness and waiting. Gravity was working, pulling denser regions of gas together, slowly building the scaffolding for what would come next. According to the Standard Model, the first stars didn't ignite until somewhere between 100 and 250 million years after the Big Bang. These were not stars like our Sun. They were monsters, hundreds of times more massive, burning blue-hot and dying young. When they exploded, they scattered the first heavy elements into space: carbon, oxygen, iron, the periodic table's rough draft. From those ashes, the next generation of stars formed, and from those stars, the first small galaxies began to assemble, slowly, piece by piece, over hundreds of millions of years. The expectation was that if you pointed a telescope powerful enough to see back to those early times, you would find small, chaotic, half-formed clumps of stars, proto-galaxies, baby galaxies, things still under construction. The Hubble Space Telescope, for all its decades of breathtaking images, could only see so far. Its instruments were tuned to visible and ultraviolet light, which meant that as it looked deeper into the universe's past, it eventually hit a wall. The most distant galaxies Hubble could detect were already redshifted so far that their light was slipping into the infrared beyond Hubble's range. And even then, those galaxies looked young, small, messy, exactly what the models predicted. Webb was built to break through that wall. Its mirror is more than 6 meters across, coated in gold to reflect infrared light with brutal efficiency. It sits at a point in space called L2, about 1.5 million kilometers from Earth, far beyond the interference of our planet's atmosphere and heat. Infrared light is what you need to see the earliest galaxies, because as the universe expands, light from distant objects gets stretched. A galaxy that emitted ultraviolet light 13 billion years ago will have that light arrive at Earth today in the infrared, redshifted by the expansion of space itself. Webb's instruments can detect wavelengths from 0.6 to 28 micrometers, which means it can see objects Hubble couldn't even dream of. objects at redshifts of 10, 12, 14 and beyond, galaxies as they existed just a few 100 million years after the Big Bang, deep in what should have been the Dark Ages. When Webb's first deep field image was released in July 2022, the immediate reaction was awe. Thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. But as astronomers began analyzing the data, the awe started curdling into confusion, because scattered throughout that image and in every deep field Webb observed afterward were galaxies that didn't fit. Galaxies sitting at redshifts corresponding to 300, 400, 500 million years after the Big Bang. Galaxies that weren't dim, scattered clumps of gas. They were massive. They had structure. Some of them had disks, some had bulges, a few even showed hints of spiral arms. These were not protogalaxies. They were fully assembled systems, the kind that in our current understanding should take several billion years to form. Not several 100 million, several billion. One of the earliest troublemakers Webb found was nicknamed Methuselah, a galaxy detected at a redshift of around 13, placing it at roughly 280 million years post-Big Bang. It wasn't the distance that caused the problem, it was what the galaxy looked like. Spectral analysis suggested it contained stars that were already old. Not newborn blue giants still burning their first hydrogen, old stars, red stars. Stars that had been around long enough to evolve off the main sequence. That should be impossible. The universe itself was only 280 million years old at that point. For a star to be old, it needs time to burn through its fuel. The smallest stars that qualify as old, stars like red dwarfs, live for trillions of years and don't age noticeably on cosmological timescales. The stars that do age within a few 100 million years are massive, and when they die, they go supernova. They don't sit quietly in a galaxy looking old and red, unless the galaxy had already gone through multiple generations of star formation, building up a population of older stars from earlier bursts, which again should take much longer than the universe had existed at that point. Then there was JWST 13-0, part of the JWST Advanced Deep Extragalactic Survey, redshift 13-2, roughly 320 million years after the Big Bang. It wasn't just bright, it was structured. Astronomers could make out regions of star formation, clumps of light distributed across the galaxy in a way that suggested organized processes, not random collapse. Structure implies time. It implies feedback, the push and pull of supernovae and stellar winds, sculpting gas clouds, triggering new waves of star formation. It implies a history. But there wasn't supposed to be enough history yet. By late 2023, the list of these troublemakers had grown. Dozens of galaxies at redshifts between 10 and 14, many of them showing masses comparable to the Large Magellanic Cloud, a satellite galaxy of the Milky Way that took billions of years to reach its current size. Some were even larger. A few had stellar masses exceeding 10 billion times the mass of the Sun, packed into galaxies the universe barely had time to sketch. The problem isn't just that these galaxies exist. It's that, under the standard model, the process of building a galaxy is slow. You start with a dark matter halo, an invisible clump of gravitational scaffolding. Gas falls into that halo and cools. It fragments into clouds. Those clouds collapse under their own gravity and ignite as stars. The stars live, die, explode, enrich the gas with heavier elements. That enriched gas cools again, forms a new generation of stars. Feedback from those stars, radiation pressure and supernova shockwaves, heats the surrounding gas and blows some of it out of the galaxy entirely. This back and forth, heating and cooling, star formation and disruption is what gradually builds up a galaxy's mass and structure over hundreds of millions, even billions of years. In the early universe, this process should have been even slower. The gas was hotter, dark matter halos were smaller. The first stars, those massive population 3 monsters, would have been incredibly disruptive, their explosions scattering more gas than they left behind. The expectation was that it would take until at least 500 million years, maybe closer to a billion, before you'd see anything resembling a well-organized galaxy. Webb found them at 300 million years, some possibly earlier, and they weren't struggling protogalaxies. They were mature systems with stellar populations, metallicity, and in some cases dust. Dust is worth pausing on, because dust doesn't exist in the early universe by default. Dust grains are made of heavy elements, carbon, silicon, oxygen, forged in the cores of stars and released when those stars die. A dusty galaxy is a galaxy that has already been through at least one, probably several, cycles of star formation and death. Dust takes time. Webb found dust in galaxies seen at 400 million years post-Big Bang. The other shock was the sheer number of these galaxies. Early estimates from Webb's first year of observations suggested there were up to 10 times more bright galaxies in the early universe than models predicted. 10 times. That's not a small adjustment you can fix by tweaking a parameter. That's a fundamental mismatch between what we expected to see and what is actually there. If galaxies were forming that early and that abundantly, something about our understanding of how structure forms in the universe is wrong. Spiral galaxies were another curveball. Spirals are delicate structures. They require a stable rotating disk of gas and stars, shaped by the balance between gravity pulling inward and angular momentum holding the disk together. In the local universe, spirals like the Milky Way took billions of years to settle into their current shapes. Early in a galaxy's life, things are chaotic, mergers are common, gas is clumpy, feedback from star formation is violent. Spiral arms shouldn't appear until a galaxy has calmed down, which happens late, not early. Webb found hints of spiral structure in galaxies at redshifts above 10. Galaxies less than 500 million years old, showing organized rotation and disk-like morphology. The images aren't perfect. Webb's resolution has limits even with its enormous mirror. But the evidence is there, encoded in the light curves and the spectral data. These galaxies are not formless blobs. They have shapes, rotation, structure. One of the researchers analyzing early Webb data described it as walking into a nursery expecting to find infants and instead finding a room full of teenagers. Not fully grown adults, but far more developed than anything that should exist at that stage. The implications are uncomfortable. Either something is accelerating galaxy formation in the early universe, some process we haven't accounted for, or the universe had more time than we think it did. If 8 billion years isn't enough time for these galaxies to form, then maybe the universe isn't 8 billion years old. That number comes from the Standard Model. It's derived from measurements of the cosmic microwave background, the expansion rate of the universe, the density of matter and energy, all plugged into equations that assume a specific history. The Planck satellite, which mapped the CMB in exquisite detail, gave us an age of 787 billion years, plus or minus 20 billion years. The error bars are tight, the confidence is high. And yet, Webb is showing us things that don't fit inside that timeline. So what do you do when the observations and the model don't agree? You can adjust the observations, assume there's some measurement error or misunderstanding in how we're interpreting the data. Or you can adjust the model, tweak the physics, Add new parameters, maybe revise how quickly dark matter clumps together or how efficiently gas cools in the early universe. Or you can do something more radical. You can ask whether the model itself, the entire framework we've built over the last century, is missing something fundamental. Whether the Big Bang, as we understand it, with its clear beginning 13.8 billion years ago, is not the whole story. There are people asking that question now, not fringe voices shouting from the internet's basement. Serious physicists and cosmologists looking at Webb's data and wondering out loud whether we've misunderstood time itself. Whether the universe's beginning, if it even had one, is something stranger and older than we ever imagined. Because the galaxies Webb is finding are not the only problem, they're just the most visible one. Underneath them, threaded through the same observations, are black holes that shouldn't exist yet, and elements that shouldn't be there. Because the galaxies Webb found are not the only problem. Sitting inside some of those galaxies, parked at the very centers like they own the place, are black holes, not small ones, not the kind you get when a massive star collapses at the end of its life. Supermassive black holes, monsters weighing 1 billion times the mass of the Sun. And they are sitting there less than 500 million years after the Big Bang, shining so brightly that we can detect them from across the entire observable universe. They should not exist yet. A black hole with 1 billion solar masses is not something you throw together over the weekend. It is the result of a long, patient, relentless process of accumulation. The standard story goes like this. A massive star, somewhere between 20 and 100 times the mass of the Sun, exhausts its fuel and collapses under its own gravity. What's left behind is a black hole weighing maybe 10 to 50 solar masses. That's your seed. From there, the black hole grows by feeding. Gas falls in. Occasionally it swallows another star. Over millions of years it gains mass. If it's sitting at the center of a forming galaxy, it has access to a steady diet of infalling material. But there's a speed limit. When a black hole feeds, the matter spiraling inward gets compressed and heated to millions of degrees. That hot gas radiates energy, producing intense light and pressure that pushes back against the infalling material. If the black hole tries to eat too fast, the radiation pressure blows the food away. This is called the Eddington limit, and it sets the maximum rate at which a black hole can grow. At that limit, a black hole roughly doubles its mass every 50 million years. So if you start with a 50 solar mass seed and grow at the absolute maximum rate allowed by physics, it takes about 1 billion years to reach 1 billion solar masses. 1 billion years, not 300 million, not 400 million, 1 billion. The universe at the time Webb is seeing these black holes was not old enough for them to have grown this way, not even close. One of the most dramatic examples is a quasar called Uhays-Ed1, detected by Webb in collaboration with the Chandra X Ray Observatory. The black hole at its center weighs somewhere in the range of a few 100 million solar masses, possibly more, and it's sitting at a redshift that places it roughly 470 million years after the Big Bang. The object is so luminous that its X-ray signature outshines the entire galaxy around it. Chandra picked up the high-energy radiation. Webb confirmed the distance. And when astronomers calculated how long it would take for a black hole that massive to grow from a stellar seed, the numbers didn't work. Even if the seed formed immediately, the moment the first stars died, and even if it fed at the Eddington limit without interruption for the entire 470 million years available, it wouldn't be big enough, not by half. Another target, a galaxy called GNZ11, sits at a redshift of about 10.6, roughly 420 million years post-Big Bang. It's one of the brightest objects Webb has observed at that distance, and spectroscopic analysis revealed something startling. Sitting at the galaxy's core is a black hole weighing around 1 million to 10 million solar masses, actively feeding. The galaxy itself is tiny, compact, with a stellar mass of maybe 1 billion suns. That means the black hole is absurdly heavy relative to the galaxy it lives in. In the local universe, the typical ratio between a supermassive black hole and its host galaxy's stellar mass is about 1 to 1,000. In GNZ 11, the ratio is closer to 1 to 100. The black hole is disproportionately massive, as if it formed first and the galaxy built itself around it later. That sequence is backwards. The standard model of galaxy formation assumes galaxies and black holes grow together. Stars form. Some of them die and leave black hole seeds. Those seeds feed on gas in the galaxy's center, growing slowly. As the black hole grows, it influences the galaxy around it. Jets of radiation and matter blast outward, heating the surrounding gas, regulating star formation. Over billions of years, a balance is reached. The black hole's mass ends up proportional to the galaxy's bulge mass. This is called black hole-galaxy coevolution, and it's one of the cleanest relationships in astrophysics. Except in the early universe, that relationship appears to be broken. The black holes are already massive when the galaxies are still small. That suggests one of two things. Either black holes can grow much faster than the Eddington limit allows, or they didn't start from stellar seeds at all. The first option, faster growth, would require a mechanism to bypass the Eddington limit. Some researchers have proposed super-Eddington accretion, where the black hole feeds in short, violent bursts, swallowing huge amounts of material in chaotic gulps before the radiation pressure has time to push back. This might happen during galaxy mergers or in extremely dense gas clouds where the black hole is buried under so much material that the radiation can't escape efficiently. There's some evidence for super-Eddington feeding in a few local systems, but it's rare and short-lived. To build a billion solar mass black hole in a few 100 million years, you'd need sustained super-Eddington accretion over almost the entire available timeline. That's not impossible, but it's pushing the boundaries of what the physics comfortably allows. The second option is more radical. Maybe these black holes didn't grow from stellar seeds at all. Maybe they were born big. This is the direct collapse scenario, and it's been around for a while, but Webb's observations have made it newly relevant. The idea is that in the very early universe, under specific conditions, a massive cloud of primordial gas, tens of thousands or even hundreds of thousands of solar masses, could collapse directly into a black hole without ever forming a star. Skip the middleman. Go straight from gas cloud to black hole. If that happened, you'd start with a seed weighing not 50 solar masses, but 100,000. From there, even growing at normal Eddington limited rates, you could reach 1 billion solar masses in the available time. Direct collapse sounds convenient, but it requires very particular conditions. The gas cloud has to be hot and dense, but also metal-free. Metals, in astronomical terms, are elements heavier than hydrogen and helium. They act as cooling agents. When a gas cloud contains even trace amounts of carbon or oxygen, those atoms radiate energy away efficiently, allowing the cloud to cool and fragment into smaller clumps. Those clumps become stars. If the gas is pristine, pure hydrogen and helium with no metals at all, it can't cool as quickly. Instead of fragmenting, the entire cloud collapses as one piece. The result is a black hole, not a star. The problem is that pristine gas clouds are supposed to be rare, even in the early universe. The first generation of stars, those massive population 3 giants, exploded as supernovae and seeded the surrounding gas with metals within the first few 100 million years. By the time you get to 400 or 500 million years post-Big Bang, most of the gas in the universe has at least some metal contamination. Finding a region pure enough for direct collapse should be difficult, and yet the black holes are there. Either direct collapse was more common than we thought, or the black holes formed through some other mechanism we haven't figured out yet. There's a third possibility that makes some physicists uncomfortable, but it's gaining traction: primordial black holes. These would be black holes that formed not from stars or collapsing gas clouds, but from density fluctuations in the first fractions of a second after the Big Bang itself. Before stars, before atoms, before anything. If the early universe had regions where matter was slightly more dense than average, those regions could have collapsed into black holes during the first moments of cosmic inflation. Primordial black holes could have any mass, from microscopic to millions of solar masses, depending on the size of the fluctuation. If they exist, and if some of them were massive, they would have been sitting in the universe from the very beginning, ready to start feeding as soon as the first gas clouds formed. That would explain why supermassive black holes appear so early. They didn't have to grow from seeds. They were already there. The idea has been around since the 1970s, proposed by Stephen Hawking and others, but it's always been speculative. We've never detected a primordial black hole directly. Webb's observations haven't proven they exist, but the data is consistent with their presence in a way that makes ignoring the possibility harder. If primordial black holes are real, they would fundamentally change the story of how structure formed in the universe. They would mean the seeds of galaxies, the gravitational anchors around which everything else assembled, were not created by stars dying. They were built into the fabric of space from the start. That shifts the timeline. It shifts the mechanism, and it raises the uncomfortable question of whether the Big Bang, as we understand it, was really the beginning or just the latest in a series of cosmic resets. But the black holes are only half the problem. The other half is chemistry. When Webb analyzed the light from these early galaxies, breaking it down into spectra to see what elements were present, it found metals, not trace amounts, significant abundances: oxygen, carbon, nitrogen, iron, elements that should not be there yet. To understand why this is a problem, you need to know where metals come from. They don't exist in the early universe. Right after the Big Bang, the universe contained hydrogen, helium, and a trace of lithium. That's it. The first three elements on the periodic table. Everything else, every atom of carbon in your body, every oxygen molecule you breathe, every iron atom in your blood was created inside stars. Stars fuse hydrogen into helium in their cores. If they're massive enough, they keep going. Helium into carbon, carbon into oxygen, oxygen into neon, magnesium, silicon. The heaviest stars build up layers like an onion, fusing heavier and heavier elements until they reach iron. At that point, fusion stops being energetically favorable. The core collapses, the outer layers explode. Supernova. All those newly forged elements scatter into space, mixing with the surrounding gas. The next generation of stars forms from that enriched gas, and they carry the chemical fingerprints of the stars that died before them. This process of metal enrichment takes time, a lot of time. The first generation of stars, population 3, lived fast and died young, maybe 3 to 10 million years per star. Their explosions seeded the gas with the first metals. The second generation, population 2 stars, formed from that slightly enriched gas and continued the cycle. By the time you get to population 1 stars, stars like our Sun, The gas has been through multiple generations of enrichment and contains a few percent metals by mass. Our Sun is about 2% metals. That 2% took billions of years to accumulate. Billions of years of stars living, dying, exploding, enriching the interstellar medium, forming new stars, repeating the process. The early universe didn't have billions of years. It had a few 100 million. And yet Webb found galaxies at redshifts of 10, 12, even higher, with metallicities that rival some galaxies in the local universe. Not pristine gas, chemically evolved gas. One of the most striking examples is a galaxy in the JWST survey, observed at a redshift of around 13, 2 corresponding to roughly 325 million years after the Big Bang. Spectroscopic analysis revealed strong oxygen emission lines, indicating that the galaxy's gas had already been enriched with significant amounts of oxygen. Oxygen is a product of massive stars. It forms in the cores of stars, more than 8 times the mass of the Sun, and it's only released into the interstellar medium when those stars go supernova. Detecting oxygen in a galaxy that young means that not only had stars already formed, lived and died, but they'd done so in numbers large enough to chemically enrich the entire galaxy. That cycle should take at minimum a few 100 million years. More realistically, closer to 1 billion. This galaxy had done it in 325 million. Another troubling case is GNZ11, the same galaxy with the oversized black hole. In addition to the black hole, Webb's instruments detected significant amounts of nitrogen in the galaxy's spectrum. Nitrogen is what astronomers call a secondary element. It's not produced in the first generation of stars. It requires carbon and oxygen to already be present in the gas before the star forms. Inside the star, nitrogen is synthesized from those pre-existing elements through a process called the CNO cycle. That means before you can have nitrogen, you need at least 2 generations of stars. First generation makes carbon and oxygen. Second generation incorporates that into new stars and makes nitrogen. Detecting nitrogen in a galaxy 420 million years after the Big Bang implies that at least 2 full cycles of stellar birth, life, death, and enrichment had already taken place. 2 cycles in 420 million years is tight, uncomfortably tight, and yet the nitrogen is there, encoded in the light, undeniable. Metallicity matters for more than just chemistry. It affects how stars form. In the local universe, metals in a gas cloud act as coolants. When a cloud starts collapsing under its own gravity, it heats up. If the gas contains carbon, oxygen, or iron, those atoms can radiate the heat away efficiently, allowing the cloud to cool and continue collapsing. That cooling is what lets the cloud fragment into smaller pieces, each of which becomes a star. Without metals, the cloud stays hot, and instead of fragmenting into many small stars, it forms one or a few very massive stars. That's why the first generation of stars were giants. No metals meant no efficient cooling, meant no fragmentation. But as soon as you introduce even small amounts of metals, the whole process changes. Star formation becomes more efficient. You get more stars per cloud, and they're smaller, longer-lived, and more stable. A metal-enriched universe forms stars differently than a metal-poor one. The early galaxies Webb is observing show evidence of efficient star formation. They're not just churning out a few massive stars and calling it a day. They're forming large populations of stars across a range of masses, enough to build up billions of solar masses of stellar material in a few 100 million years. That efficiency requires metals, but the metals require stars to have already formed, died, and exploded. You have a chicken and egg problem, but worse, because both the chicken and the egg need to have already gone through several generations before you're even allowed to ask which came first. There's another wrinkle: dust. Dust grains in space are tiny particles, typically a fraction of a micrometer across, made of carbon, silicon, and oxygen. They form in the cool outer atmospheres of dying stars and in the expanding shells of supernova remnants. Dust is important because it absorbs ultraviolet light from young stars and re-radiates it in the infrared. It also provides surfaces where molecules can form, including molecular hydrogen, which is critical for star formation. Dust is a sign of chemical maturity. It means a galaxy has been recycling gas and heavy elements for a substantial amount of time. Webb detected dust in galaxies at redshifts above 10. Dust in a galaxy less than 500 million years old. That dust didn't appear by magic. It was manufactured by stars that had already lived and died, stars that themselves required earlier generations to have enriched the gas with the raw materials. Dust is the final product of a long assembly line, and finding it in the cosmic equivalent of a newborn nursery is like discovering a smartphone in an archaeological dig dated to the Bronze Age. So we have galaxies forming too early, black holes too massive too soon, chemistry too advanced for the available timeline, and the universe is supposedly 8 billion years old, an age we've calculated with extraordinary precision using the cosmic microwave background. The expansion rate, the density of matter and dark energy, all of it. The error bars are tight, the model is robust, the observations should fit, they don't. You can try to tweak the model. Maybe star formation was more efficient in the early universe than we assumed. Maybe black holes grew faster through mechanisms we haven't fully explored. Maybe the first stars were different enough that they enriched the gas more quickly. Each adjustment buys you a little time, makes the timeline slightly less impossible, but every adjustment has costs. Make star formation too efficient, and you overproduce metals, which changes how later galaxies form. Make black holes grow too fast, and you have to explain why they don't keep growing uncontrollably today. Each fix creates a new tension somewhere else in the model. Or you can ask a different question. What if the timeline itself is the problem? What if 8 billion years is not the whole story? What if the Big Bang, that singular explosive beginning we've anchored everything to, is not the beginning at all, but a transition, a reset point in a much older, possibly infinite process? That question is not new. It's been whispered at the edges of cosmology for decades. But for most of that time, it's been easy to ignore because the standard model worked so well. The data fit. The predictions were confirmed. There was no need to reach for exotic alternatives. Webb changed that, not because it disproved the Big Bang, but because it found things that the Big Bang framework struggles to explain, things that point backward, past the supposed origin, toward something older. And there is a physicist who has been arguing for exactly that possibility for more than 15 years. A man who won the Nobel Prize for his work on black holes, who has spent the better part of his career proposing that the universe did not begin 8 billion years ago. That time does not have a starting point, and that what we call the Big Bang is just one beat in an eternal cycle. His name is Roger Penrose, and his ideas have gone from fringe speculation to something cosmologists are starting to take seriously because the data Webb is collecting fits uncomfortably well into the framework he's been building all along. And there is a physicist who has been arguing for exactly that possibility for more than 15 years. A man who won the Nobel Prize for his work on black holes, who has spent the better part of his career proposing that the universe did not begin 13.8 billion years ago. That time does not have a starting point, and that what we call the Big Bang is just one beat in an eternal cycle. His name is Roger Penrose, and his ideas have gone from fringe speculation to something cosmologists are starting to take seriously, because the data Webb is collecting fits uncomfortably well into the framework he's been building all along. Roger Penrose is not easy to categorize. He is 93 years old as of this writing, a mathematical physicist whose career has spanned more than 6 decades and whose contributions to our understanding of space-time, black holes, and the structure of the universe place him firmly among the most important scientists of the 20th and 21st centuries. In 2020, he was awarded the Nobel Prize in Physics, sharing it with Reinhard Genzel and Andrea Ghez for his theoretical work proving that black holes are a direct consequence of Einstein's general theory of relativity. That work, done in the mid-1960s, was groundbreaking. It showed that under very general conditions, a collapsing star must form a singularity, a point where the curvature of space-time becomes infinite and the known laws of physics break down. Before Penrose's proof, it was possible to argue that black holes were mathematical curiosities, flukes that arose only under very specific, artificially symmetric conditions. Penrose closed that loophole. He demonstrated that singularities are generic, inevitable features of gravitational collapse. If you have enough mass in a small enough space, a black hole will form. Not might, will. That contribution alone would have been enough to secure his legacy. But Penrose did not stop there. Throughout his career, he has developed a reputation for thinking sideways, for approaching problems from angles that make other physicists uncomfortable. He worked with Stephen Hawking in the 1970s to extend the singularity theorems to cosmology itself, showing that if general relativity is correct and the universe is expanding, then running the clock backward leads inevitably to a singularity at the beginning. The Big Bang singularity, a point of infinite density and temperature where space-time itself begins. Most physicists took that result and moved on, accepting the Big Bang as the origin of everything. Penrose looked at it and thought, that doesn't make sense. Singularities, in Penrose's view, are places where the theory breaks down. They are not physical objects. They are signals that something is missing from our understanding. The singularity at the center of a black hole is hidden behind an event horizon, sealed off from the rest of the universe, so we can live with not knowing what happens there. But the Big Bang singularity is different. It is not hidden. It is in our past. It is the foundation of everything we see. And if the laws of physics break down at that point, then we have no right to claim we understand where the universe came from. Penrose spent years thinking about that problem. He considered whether quantum mechanics might smooth out the singularity, whether some new physics might take over at those extreme scales and avoid the breakdown. But the more he thought about it, the more convinced he became that the singularity was not the real problem. The problem was the assumption that the Big Bang was a beginning at all. In 2006, Penrose published a paper in the Proceedings of the Royal Society of London laying out a new cosmological model. He called it Conformal Cyclic Cosmology, CCC for short. The idea was radical, and Penrose knew it. In interviews, he has described it as crazy, unconventional, difficult to sell to the broader community. But he also believed it solved problems that the standard model could not, and that it made predictions which could, in principle, be tested. The central idea of CCC is deceptively simple. The universe does not have a beginning. What we call the Big Bang is not the origin of time and space. It is a transition, a crossover point between two phases of an eternal process. Before our Big Bang, there was another universe, an earlier aeon, that had expanded and cooled and emptied out over trillions upon trillions of years until it reached a state where it was composed almost entirely of massless particles, photons, gravitons, radiation drifting through an ever larger, ever colder void. And in that state, something remarkable happens. The universe loses its sense of scale. Penrose's insight hinges on a concept from geometry called conformal invariance. In mathematics, a conformal transformation is one that preserves angles but not distances. You can stretch or shrink a shape, but as long as the angles between lines stay the same, the transformation is conformal. Certain physical theories, particularly those involving only massless particles, are conformally invariant. That means the equations describing those theories do not change if you rescale all distances by the same factor. If the universe contains only massless particles, there is no way to define an absolute scale. A photon traveling through empty space has no internal clock that tells it how big the universe is. It just travels forever. And if there is nothing in the universe with mass, nothing to provide a reference scale, then the geometry of that universe becomes ambiguous. Penrose realized that the far future of our universe, if current cosmological models are correct, will eventually become a state of exactly this kind. Stars will burn out, galaxies will drift apart, black holes will evaporate through Hawking radiation over unimaginable timescales. Eventually, after 10 to the 100 years or more, the universe will contain nothing but photons and gravitons, particles with no mass, drifting through an exponentially expanding void. At that point, the universe will have no memory of how big it used to be. Distances will still exist in some formal sense, but they will be meaningless because there is nothing to measure them against. The geometry will be described entirely by angles and light paths, not by lengths or scales. And here is the leap. If the far future of one universe is a cold, empty, massless, conformally invariant state, and if the Big Bang of the next universe is a hot, dense, conformally invariant state, then mathematically those two states are the same. You can take the equations describing the end of one aeon, apply a conformal transformation, and get the equations describing the beginning of the next. The infinite future of one universe maps directly onto the Big Bang of another. There is no singularity. There is no beginning. There is just a boundary, a crossover, where the geometry of space-time transitions smoothly from one aeon to the next. It sounds like magic, but the mathematics is rigorous. Penrose laid it out in detail in his 2010 book Cycles of Time, and later in his 2016 work Fashion, Faith and Fantasy. The key is that at the crossover, all particles are massless, or effectively so. Mass is what gives particles their sense of time. A massive particle has a rest frame. It ages. It experiences proper time. A massless particle does not. A photon, from its own perspective, travels instantaneously from emission to absorption. It does not age. It experiences no time. If the universe is composed entirely of such particles, then the concept of time becomes ambiguous. The far future of one aeon, stretched out over infinite time, and the hot, dense beginning of the next, compressed into an instant, become geometrically indistinguishable. Penrose's model does not require new particles or new forces. It does not invoke extra dimensions or multiverses. It uses only general relativity and the properties of massless fields. That is part of its appeal. It is a conservative extension of known physics, not a speculative leap into the unknown. But it requires a willingness to let go of the idea that the Big Bang was a beginning, and that is not an easy thing to do. The Big Bang has been the foundation of cosmology for nearly a century. It is built into the language, the models, the way we think about time itself. To say that it was not a beginning, that it was just a transition, feels like pulling the rug out from under the entire field. Penrose faced serious resistance when he first proposed CCC. The default cosmological model at the time, and still today, is lambda CDM, which includes inflation, dark matter, dark energy, and a singular Big Bang origin. Inflation, in particular, is the reigning paradigm for explaining the large-scale uniformity of the universe. It posits that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, smoothing out any initial irregularities and setting the stage for the structure we see today. Inflation has been enormously successful at explaining observations, and it has become the lens through which most cosmologists interpret the data. CCC rejects inflation. Penrose has been vocal about this. He argues that inflation is an ad hoc solution, a patch added to the standard model to explain why the universe looks so smooth and flat. It works, but it requires fine-tuning the initial conditions in ways that feel unsatisfying. More fundamentally, inflation does not explain where the Big Bang came from. It just pushes the question back one step. If the universe inflated, what set up the conditions for inflation? What came before? The standard answer is that we cannot know, that the singularity at the Big Bang is a wall we cannot see past. Penrose finds that answer unacceptable. CCC offers an alternative. The uniformity of the universe is not the result of a brief inflationary burst. It is inherited from the previous aeon, smoothed out over trillions of years of expansion and cooling. The Big Bang is not a beginning. It is a reset. The resistance Penrose faced was not just ideological. There were technical objections. One of the most serious is the second law of thermodynamics. Entropy, the measure of disorder in a system, always increases over time. That is one of the most robust laws in physics. It means the universe is constantly moving from order to disorder, from low entropy to high entropy. The early universe, just after the Big Bang, was in a state of extraordinarily low entropy. Everything was smooth, uniform, simple. As the universe evolved, structure formed. Stars, galaxies, black holes, all of which represent increases in entropy. Eventually, the universe will reach a state of maximum entropy, a cold, featureless expanse where nothing interesting can happen. That is the heat death, the far future endpoint of standard cosmology. CCC requires that after the heat death of one aeon, the next aeon begins in a low entropy state again. But how? How do you reset entropy? The second law says you cannot. Once entropy increases, it stays increased. That is the whole point. Penrose's answer is subtle. He argues that in the far future, when all particles are massless and the universe has no sense of scale, the concept of entropy becomes ill-defined. Entropy is a statistical measure that depends on counting microstates, the different ways particles can be arranged. But if the particles have no mass and the universe has no scale, then the number of available microstates changes. Black holes, which are the largest contributors to the universe's entropy, have evaporated. Their entropy, encoded in the area of their event horizons, is gone. What is left is a universe of photons, and the entropy of a gas of massless photons in an expanding universe does not behave the same way as the entropy of a universe filled with matter and black holes. Penrose claims that at the conformal crossover, the entropy effectively resets, not by violating the second law, but by redefining what entropy means in a massless, scale-free geometry. Not everyone buys this argument. Critics point out that even if black holes evaporate, the information they contained, the entropy, has to go somewhere. Hawking radiation carries it away, but it does not disappear. The universe at the end of one aeon should still be in a high entropy state, and no amount of conformal rescaling should change that. Penrose's response is that the details depend on quantum gravity, a theory we do not yet have. and that CCC makes assumptions about how information and entropy behave at the conformal boundary that are consistent with known physics but not yet proven. It is a gap in the model, and Penrose acknowledges it, but he also points out that the standard Big Bang model has its own entropy problem. Why was the entropy of the universe so low at the Big Bang? The standard answer is that it just was, that the initial conditions were fine-tuned for reasons we do not understand. CCC at least offers a mechanism, even if the details are not fully worked out. Another objection is more philosophical. If the universe is eternal, cycling through infinite aeons, then where did it come from? What started the cycle? Penrose's answer is that the question does not make sense. Time in CCC has no beginning. There is no first aeon. The cycle has always been running. That might feel unsatisfying, but it is not obviously worse than the alternative, which is that time began at the Big Bang for no reason. Either way, you are left with a brute fact, something that exists without explanation. The question is which brute fact you find more palatable, an eternal cycle with no beginning, or a singular origin that emerged from nothing. Penrose is comfortable with the eternal cycle. He has said in interviews that the idea of a beginning, a moment when time itself starts, feels arbitrary to him. He is not religious. He does not believe in a creator, and he is suspicious of models that require initial conditions to be fine-tuned to extraordinary precision without any explanation for why they were that way. CCC, in his view, is more elegant because it does not require the universe to have been set up just so at the beginning. The conditions at the start of each aeon are the natural result of the end of the previous aeon. Everything follows from the dynamics, not from some mysterious initial setup. But elegance is not enough. Physics is an empirical science. Models have to make predictions that can be tested, and this is where CCC gets interesting, because Penrose claims it does make predictions. Specific predictions. Predictions that, as of 2020, have been tested and, according to him, confirmed. The key prediction involves the cosmic microwave background, the faint glow of radiation left over from when the universe was 380,000 years old. The CMB is one of the pillars of the Big Bang model. It is extraordinarily uniform, with temperature variations of only a few parts per 100,000. Those tiny variations are the seeds of all the structure we see today, the galaxies and clusters and voids. In the standard model, the CMB is a snapshot of the moment the universe became transparent to light, and the pattern of hot and cold spots reflects quantum fluctuations from the inflationary period stretched to cosmic scales. In CCC, the CMB also reflects the previous aeon. Specifically, it should contain imprints of the most violent energetic events from the previous universe. And the most violent energetic events are collisions between supermassive black holes. When two black holes spiral together and merge, they release an enormous amount of energy in the form of gravitational waves. In the previous aeon, these mergers would have occurred over trillions of years as galaxies collided and their central black holes coalesced. Each merger would have sent a burst of gravitational radiation rippling outward through space. By the time the aeon ended and the conformal crossover occurred, those ripples would have been stretched to enormous scales. And as the geometry transitioned into the next aeon, the ripples would have left an imprint on the CMB, a pattern of concentric circles, like ripples on a pond, centered on the point in the sky where the merger occurred. Penrose calls these patterns Hawking points, named after Stephen Hawking, his collaborator and friend, who passed away in 2018. Hawking points are not random, they are highly specific. Each one should appear as a set of concentric rings in the CMB temperature map, slightly hotter or cooler than the surrounding average, with the rings spaced in a way that reflects the properties of the black hole merger that created them. If CCC is correct, The CMB should be full of these patterns, dozens or hundreds of them, scattered across the sky. If CCC is wrong, they should not be there. In 2020, Penrose and a team of collaborators published a paper in the monthly notices of the Royal Astronomical Society claiming they had found the Hawking points. Using data from the Wilkinson Microwave Anisotropy Probe, WMAP, a satellite that mapped the CMB between 2001 and 2010, they identified regions of the sky where the temperature pattern matched the predicted signature of a Hawking point. They ran statistical tests to determine whether the patterns could have arisen by chance, and they concluded that the probability was extremely low. According to their analysis, the Hawking points were real, detected at a confidence level of 99.98%. That claim was explosive. If true, it would be the first direct observational evidence for CCC, and it would imply that the universe did not begin with the Big Bang. It would mean we are living in at least the second aeon, possibly the trillionth, with no way to know how far back the cycle extends. The implications would be staggering, not just for cosmology, but for philosophy, for our understanding of time and existence itself. The paper was met with skepticism. Other cosmologists pointed out that the CMB is full of patterns, and that with enough searching, you can find almost anything if you are not careful about how you define your search criteria. The statistical tests Penrose's team used were questioned. Some researchers tried to replicate the analysis and came up with different results, arguing that the Hawking points could be explained as random noise or as artifacts of the way the data was processed. The debate is ongoing. As of now, the existence of Hawking points is not widely accepted, but it is also not dismissed. The fact that a Nobel laureate was willing to stake his reputation on the claim, and that the statistical analysis showed such a high confidence level, has forced the community to take it seriously. Penrose, for his part, has continued to refine his model and defend his results. He has given talks, written papers, appeared in interviews and documentaries explaining CCC to broader audiences. He has a calm, unhurried way of speaking, the demeanor of someone who has spent decades thinking deeply about a problem and is confident but not dogmatic about his conclusions. He acknowledges the resistance. He knows his ideas are unconventional, but he also believes the evidence is on his side and that as more data comes in, particularly from Webb, the case for CCC will strengthen. Because here is the thing: the galaxies Webb is finding, the massive black holes, the advanced chemistry, all of it fits more naturally into a cyclic model than into a singular Big Bang. If the universe is only 13.8 billion years old, then everything Webb is seeing had to happen in a narrow, frantic window of time. Star formation, black hole growth, chemical enrichment, all of it compressed into a few 100 million years. The timelines are tight. The mechanisms are strained. Every new observation from Webb makes the standard model work a little harder to explain what it is seeing. But if CCC is correct, then the early universe was not starting from scratch. The structures Webb is observing, the galaxies and black holes, could have inherited mass and angular momentum from the previous aeon. The seeds of structure were already there, encoded in the geometry of the conformal crossover. The timeline is no longer a problem because the process did not begin 13.8 billion years ago. It began trillions of years earlier, in the previous aeon, and the current aeon is just continuing a process that has been running forever. The black holes did not have to grow from stellar seeds in a few 100 million years. They were already massive at the crossover, carried forward from the previous cycle. The galaxies did not have to form from scratch. They assembled from structures that were already partially built. The chemistry did not have to start from pure hydrogen and helium. There were metals already present, remnants of stars that lived and died in the previous universe, their atoms stretched and recycled through the conformal boundary into the next aeon. None of this is proven. CCC is still a speculative model, and Penrose would be the first to admit that. But it is a model that makes testable predictions, and those predictions are being tested right now. Webb is not looking for Hawking points. It is not designed to map the CMB, but every deep field image it captures, every spectrum it analyzes, every galaxy and black hole it finds in the early universe is a data point that either supports or challenges the standard timeline. And so far, the data has been challenging. Penrose is 93 years old. He has spent the last 2 decades of his life developing and defending a cosmological model that most of his peers consider unlikely at best. He has taken risks, published provocative papers, made bold claims, and now, as Webb continues to peer into the earliest moments of cosmic history, his ideas are finding a strange new relevance, because the universe Webb is revealing is not the universe we expected to see. It is older in a sense, more developed, more structured, and if Penrose is right, that is because it had a head start we never accounted for. Because what we call the beginning was not a beginning at all. It was an echo of something that came before. And that echo, if we know where to look, might still be visible, encoded in the faint glow of radiation that has been traveling toward us for more than 13 billion years. Because here is where the story gets uncomfortable for everyone involved. Penrose did not just build a theoretical model and walk away. He went looking for proof, not in the distant reaches of space where Webb is now scanning for early galaxies, not in particle accelerators or gravitational wave detectors. He went looking in a place cosmologists have been staring at for decades, a place they thought they understood completely. The cosmic microwave background, the afterglow of the Big Bang, the most studied, most mapped, most analyzed piece of light in the history of astronomy. And according to Penrose, it has been hiding a secret the entire time. The cosmic microwave background, the CMB, is everywhere. Right now, as you sit wherever you are, faint microwave radiation is passing through you from every direction. It fills the entire sky uniformly, a glow so faint and so cold that it took until 1964 to detect it by accident. 2 radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate noise from a horn antenna and kept picking up a persistent hiss. They checked everything. They cleaned out pigeon droppings. They pointed the antenna in different directions. The hiss remained constant and unchanging, coming from everywhere at once. What they had found was the thermal echo of the Big Bang itself, cooled over 13.8 billion years of cosmic expansion to a temperature of just 2.73 Kelvin, barely above absolute zero. The discovery earned them the Nobel Prize in 1978. It was one of the most important confirmations of the Big Bang model. If the universe began in a hot, dense state and has been expanding and cooling ever since, there should be leftover radiation from that early phase, stretched by the expansion into the microwave range. And there it was, exactly where the theory predicted. For decades after the discovery, physicists worked to measure the CMB in greater and greater detail. Early observations showed that it was almost perfectly uniform. The temperature was the same in every direction to within a few parts per 100,000. That uniformity was itself a puzzle. How did regions of the universe on opposite sides of the sky, regions that had never been in contact with each other because light had not had time to travel between them, end up at the same temperature? That puzzle was one of the motivations for inflation, the idea that the universe underwent a brief period of exponential expansion in its first fraction of a second, smoothing out any initial irregularities. But the CMB is not perfectly uniform. In 1992, NASA's COBE satellite, the Cosmic Background Explorer, detected tiny variations in the temperature of the CMB, hot spots and cold spots, deviations of only a few millionths of a degree. Those variations are the seeds of all structure in the universe. The hotspots correspond to regions where the density of matter was slightly higher in the early universe. Those denser regions eventually collapsed under gravity to form galaxies and clusters. The cold spots correspond to regions where the density was slightly lower, which became the voids between galaxy clusters. The pattern of hot and cold spots encodes information about the conditions in the universe when it was only 380,000 years old, long before stars or galaxies existed. By the early 2000s, the CMB had been mapped in extraordinary detail. The Wilkinson Microwave Anisotropy Probe WMAP launched in 2001 and spent 9 years mapping the sky. It produced a temperature map of the entire CMB with a resolution of about 0.2 degrees, roughly the size of the Moon as seen from Earth. The map revealed the hot and cold spots in exquisite detail, and physicists used it to extract cosmological parameters with astonishing precision. The age of the universe, the density of matter and dark energy, the rate of expansion. The data fit the lambda CDM model, the standard Big Bang framework, almost perfectly. Every prediction matched. Every parameter landed within the expected range. The CMB became the crown jewel of observational cosmology. It was proof that we understood the universe's history. Then, in 2010, Roger Penrose published a paper with Vaha Gurzadian, a physicist at the Yerevan Physics Institute in Armenia, claiming they had found something in the WMAP data that no one else had noticed, or more accurately, something everyone else had dismissed as noise. Concentric circles. Sets of rings in the CMB temperature map, centered on specific points in the sky, with each ring slightly hotter or slightly cooler than the surrounding average. The circles were faint. They were not obvious. You had to know what you were looking for and apply specific statistical tests to pull them out of the data. But according to Penrose and Gurzadian, they were there, and they were not random. The paper was submitted to Physical Review Letters, one of the most prestigious physics journals in the world. It was rejected. The reviewers said the statistical analysis was not rigorous enough, that the patterns could easily arise by chance in random noise, and that the claim was extraordinary enough to require extraordinary evidence. Penrose revised the paper and submitted it to a different journal, the International Journal of Modern Physics D, where it was published in 2011. The title was straightforward. Concentric circles in WMAP data may provide evidence of violent pre-Big Bang activity. The claim was anything but. Penrose's argument was this: if conformal cyclic cosmology is correct, then the CMB is not just a snapshot of the early universe. It is also a record of the late stages of the previous aeon. Specifically, it should contain the imprints of the most energetic events from that previous cycle, and the most energetic events by far are the collisions and evaporations of supermassive black holes. In the previous aeon, as galaxies drifted apart and stars burned out, supermassive black holes would have been left behind, sitting at the centers of dead galaxies, slowly evaporating through Hawking radiation. Hawking radiation is a quantum process where black holes emit particles and lose mass over time. For a stellar mass black hole, the evaporation time is longer than the current age of the universe by many orders of magnitude. But for a supermassive black hole weighing billions of solar masses, the evaporation time is even longer, trillions upon trillions of years, far into the future of the previous aeon. When two supermassive black holes finally evaporated completely, The last burst of Hawking radiation would have been enormous, a final explosive release of energy as the black hole's event horizon shrank to zero and the remaining mass converted into radiation. Penrose calls this final moment a Hawking point. The radiation from that event would have propagated outward through the previous aeon as a spherical wave, a ripple in spacetime. As the aeon aged and the universe expanded and cooled, that ripple would have been stretched to larger and larger scales. By the time the conformal crossover occurred, the ripple would have been imprinted on the geometry of spacetime itself. And as that geometry transitioned into the next aeon, our aeon, the ripple would have left a mark on the CMB. A set of concentric circles, like the ripples you see when you drop a stone into still water. Each Hawking point, each evaporated black hole from the previous aeon, should produce its own set of circles in the CMB. The spacing between the rings depends on the mass of the black hole and the timing of its evaporation. The amplitude, the temperature difference between the rings and the background, depends on how much energy was released. If Penrose is right, the CMB should be dotted with these patterns, scattered across the sky, each one a fossil from the previous universe. A message written in the geometry of spacetime, carried forward through the conformal boundary into our present. Penrose and Galaxies claimed they had found them. Using the WMAP 5-year data release, they identified multiple sets of concentric circles, far more than would be expected from random fluctuations. They applied a statistical test called the Wilcoxon rank sum test, which compares the temperature variations along concentric rings to the variations in nearby regions of the CMB. If the rings are real, the variations along the rings should be systematically different from the background. Their analysis found that the probability of the observed patterns arising by chance was less than 0.02%. In other words, the circles were statistically significant. They were real features of the CMB, not artifacts or noise. The claim was explosive. If confirmed, it would be the first direct observational evidence for a universe before the Big Bang. It would mean the CMB, the most studied map in all of cosmology, had been hiding proof of conformal cyclic cosmology for decades. The implications were staggering, not just for cosmology, but for the entire structure of time and existence. The universe did not begin, it cycled, and we were living in one iteration of an eternal process. The response from the cosmology community was swift and skeptical. Within months, multiple independent teams published papers challenging the claim. The most detailed rebuttal came from Adam Moss, Douglas Scott, and James Webb, cosmologists at the University of British Columbia. They took the same WMAP data Penrose and Galaxies had used and ran their own analysis. They generated thousands of simulated CMB maps, artificial skies with the same statistical properties as the real CMB, but created from pure random noise. Then they applied the same statistical test Penrose had used, searching for concentric circles in the simulated maps. What they found was that the circles appeared just as often in the random simulations as they did in the real data. The patterns Penrose had identified were not special. They were exactly what you would expect to find if you searched hard enough through any map with the statistical structure of the CMB. The circles were not signals, they were noise. Moss, Scott, and Webb published their results in 2011 in the Journal of Cosmology and Astroparticle Physics. The title was blunt: "No evidence for anomalously low variance circles on the sky." Their conclusion was equally blunt. The concentric circles detected by Penrose and Galaxies do not provide evidence for pre-Big Bang physics. They are consistent with the standard inflationary lambda CDM model. The statistical significance claimed in the original paper is not robust. When proper controls are applied, the patterns disappear. Other teams reached similar conclusions, Amir Hajian, a physicist at Princeton, ran his own analysis and found that the number of circles in the WMAP data was entirely consistent with random chance. No anomaly, no signal, just the kind of patterns that naturally arise when you apply sensitive statistical tests to noisy data. The CMB is full of structure, hot spots and cold spots, distributed across the sky in a way that looks random at first glance, but is actually the result of specific physical processes in the early universe. If you look hard enough, you can find almost any pattern you want: faces, animals, geometric shapes. The human brain is wired to find patterns even when none exist. Scientists are not immune to this. That is why rigorous statistical controls are necessary. You have to compare your findings to simulations, to random data, to null hypotheses. You have to prove that what you are seeing is not just a product of the search method itself. Penrose pushed back. He argued that the critics were misapplying the statistical tests, that they were not accounting for the specific properties of the Hawking points, that their simulations did not fully capture the structure predicted by CCC. He and Gurzadian published follow-up papers refining their analysis, using different statistical methods, applying more stringent criteria. In 2013, they published another paper claiming they had found additional evidence in the WMAP 7-year data release. They identified what they called low-variance circles, regions where the temperature fluctuations along concentric rings were unusually smooth compared to the surrounding CMB. According to their analysis, there were too many of these low-variance circles to be explained by chance. The probability was less than 0.1%. Again, independent teams checked the claim. Again, they found that the patterns were consistent with random noise. The European Space Agency's Planck satellite, which launched in 2009 and produced the most detailed map of the CMB ever made, released its final results in 2018. The Planck team explicitly searched for the kinds of anomalies Penrose had claimed to find: concentric circles, Hawking points, low-variance regions. They found nothing. No statistically significant deviations from the standard lambda CDM model. No evidence for pre-Big Bang structures imprinted on the CMB. The Planck data, with its higher resolution and more sensitive instruments, should have made the circles easier to detect if they were real. Instead, they vanished. This is where the story gets messy, because Penrose is not a crank. He is not some internet conspiracy theorist with a YouTube channel and no credentials. He is a Nobel Prize-winning physicist with decades of experience in general relativity and cosmology. His work on singularities and black holes is foundational. He has collaborated with Stephen Hawking. He has published in the most prestigious journals, and yet he is making a claim that the overwhelming majority of his peers do not accept. A claim that has been tested multiple times by independent groups and has failed every test. That is a deeply uncomfortable situation for everyone involved. From Penrose's perspective, the rejection is frustrating. He believes the standard cosmology community is too wedded to the lambda CDM model to seriously consider alternatives. He thinks the statistical methods used by his critics are missing the point, that they are testing for the wrong kind of signal. He has said in interviews that the circles are subtle, that they require careful analysis to detect, and that most cosmologists are not willing to put in the effort because they assume CCC is wrong from the start. There is some truth to that. Science is a conservative enterprise. New ideas face high barriers, and they should. Extraordinary claims require extraordinary evidence. But that conservatism can also become inertia. If a model works as well as lambda CDM does, there is little incentive to explore alternatives, especially if those alternatives require rethinking fundamental assumptions about time and beginnings. From the critic's perspective, Penrose is engaging in a classic case of pattern matching. He has a theory, CCC, and he is searching the data for patterns that fit the theory. When you do that, especially with a dataset as rich and complex as the CMB, you will find patterns. The question is whether those patterns mean anything. The statistical tests are designed to answer that question, and so far every rigorous test has said no. The circles are not anomalies, they are noise. The Planck satellite, with better data and better resolution, should have settled the question. It did not find the circles. That is as close to a definitive answer as you can get in observational cosmology. But there is a third perspective worth considering. The absence of evidence is not always evidence of absence. The CMB is an incredibly rich dataset, and our tools for analyzing it are constantly improving. It is possible, though unlikely, that there are real signals buried in the noise that we have not yet figured out how to extract properly. CCC makes specific predictions about what those signals should look like: concentric circles, low variance regions, specific angular scales, specific amplitudes. If someone someday finds a robust, reproducible detection of those patterns, using methods that pass peer review and survive independent replication, then the conversation changes. Until that happens, the scientific consensus is clear. The circles are not there. The Hawking points are not there. The CMB does not show evidence of a pre-Big Bang aeon. Penrose has not given up. In 2020, he published yet another paper with a larger team, this time using both WMAP and Planck data, refining the search algorithms and applying more sophisticated statistical tests. The paper identified multiple candidate Hawking points and claimed, once again, that the probability of these patterns arising by chance was vanishingly small. The paper was published in the monthly notices of the Royal Astronomical Society, a respected journal, though not without controversy. Some reviewers remain unconvinced. The debate continues. What makes this story fascinating is not just the science, but the human element. Penrose is in his 90s. He has spent the better part of 2 decades developing and defending CCC, writing books, giving lectures, publishing papers that are met with skepticism and sometimes outright dismissal. He knows he is fighting an uphill battle, and yet he persists because he believes the evidence is on his side and because he thinks the standard model, for all its successes, is missing something fundamental. Whether he is right or wrong, his willingness to challenge the consensus, to stake his reputation on an unpopular idea, is worth something. Science needs people like that. Not because every Maverick is correct, but because progress requires someone to ask uncomfortable questions. The CMB is not done teaching us things. It is the oldest light we can see, the furthest back we can look without hitting the opaque wall of the early plasma. Every improvement in telescope technology, every refinement in data analysis reveals new details. The temperature map is now known to extraordinary precision. The polarization patterns, the way the CMB light is oriented as it travels through space, are being mapped and analyzed. These polarization patterns encode information about gravitational waves from the early universe, about the geometry of space-time, about processes that happened in the first fractions of a second after the Big Bang, or, if Penrose is right, about processes that happened in the aeon before. One of the challenges with detecting Hawking points is that they are predicted to be very faint. The temperature differences between the rings and the background are only a few millionths of a degree, buried under the much larger fluctuations from the standard inflationary signals. Pulling them out requires not just sensitive instruments, but also sophisticated algorithms that can distinguish between different kinds of patterns. The statistical methods Penrose and his collaborators have used are controversial because they involve a lot of choices. Which regions of the sky to search, what angular scales to focus on, how to define a circle, how to measure significance. Each choice introduces the possibility of bias. If you tune your search criteria to match what you expect to find, you will find it, even if it is not really there. That is why independent replication is so important. Someone else, using different methods, different data, should be able to find the same signal if it is real. So far, that has not happened. The Planck team, using the best data available, did not find Hawking points. That is a strong result. It does not prove CCC is wrong, but it does mean that if the circles are real, they are even fainter and more subtle than Penrose predicted. That makes them harder to test, and it weakens the empirical case for the model. You can always adjust a theory to fit the data by making its predictions vaguer or harder to detect. But at some point, that stops being science and starts being unfalsifiable speculation. CCC has not crossed that line yet, but it is walking close to the edge. There is another possibility that has not been explored as thoroughly. What if the circles are real, but they are not Hawking points? What if there is some other process, something within the standard model, that produces concentric ring patterns in the CMB? Gravitational lensing, for example, can distort the CMB light as it travels through space, bending it around massive galaxy clusters. Could lensing produce ring-like patterns? Probably not at the scales Penrose is talking about, but the question is worth asking. Cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe, could also leave patterns in the CMB. They have never been detected, but if they exist, they might produce circular or linear features that could be mistaken for Hawking points. The point is that even if Penrose's circles are real, they do not automatically prove CCC. You have to rule out every other possible explanation first. That is the burden of proof for any extraordinary claim, and CCC is an extraordinary claim. It requires accepting that the universe is eternal, that the Big Bang was not a beginning, that time does not have a starting point. It requires accepting that black holes evaporated in a previous aeon left imprints that survived the conformal crossover into our aeon. It requires accepting that the CMB, which fits the standard model so well, also contains hidden signals that only CCC predicts. That is a lot to accept on the basis of contested statistical patterns in a noisy dataset. It is not impossible. It is just not where the evidence currently points. Penrose's supporters will argue that the evidence is still coming in, that Webb is finding things, massive galaxies and black holes in the early universe, that do not fit comfortably into the standard timeline. That the Hubble tension, the disagreement over the expansion rate, suggests something is wrong with lambda CDM. That all of these cracks, taken together, point toward a model like CCC. Maybe. Or maybe they point towards some other modification of the standard model, something less radical, something that does not require infinite cycles of cosmic reincarnation. The next few years will be critical. Webb is going to keep observing. More data will come in. More early galaxies, more black holes, more chemical abundances. If the tensions keep growing, if the standard model keeps struggling to explain what Webb is seeing, then alternatives like CCC will get more attention. Not because Penrose found circles in the CMB, but because the overall structure of the observations demands a new framework. The CMB itself is unlikely to provide the decisive evidence. It has been mapped as thoroughly as current technology allows. Future missions might push the sensitivity higher, might detect fainter signals in the polarization patterns or the secondary anisotropies, the tiny distortions caused by later events like galaxy clusters. But the concentric circles, the Hawking points, if they exist, are at the very edge of detectability. They are not going to jump out of the data and announce themselves. They will remain ambiguous, contested, a footnote in the story of CCC rather than its smoking gun. The real test of CCC will come from somewhere else, from the galaxies Webb is finding, from the black holes that should not exist yet, from the chemistry that appeared too soon. If those observations keep piling up, if the standard model cannot stretch far enough to accommodate them, then Penrose's broader idea that the universe is older than we think, that it did not begin with the Big Bang, starts to look less like a Maverick's fantasy and more like a possibility worth taking seriously. The CMB itself is unlikely to provide the decisive evidence. It has been mapped as thoroughly as current technology allows. Future missions might push the sensitivity higher, might detect fainter signals in the polarization patterns or the secondary anisotropies, the tiny distortions caused by later events like galaxy clusters. But the concentric circles, the Hawking points, if they exist, are at the very edge of detectability. They are not going to jump out of the data and announce themselves. They will remain ambiguous, contested, a footnote in the story of CCC rather than its smoking gun. The real test of CCC will come from somewhere else, from the galaxies Webb is finding, from the black holes that should not exist yet, from the chemistry that appeared too soon. If those observations keep piling up, if the standard model cannot stretch far enough to accommodate them, then Penrose's broader idea that the universe is older than we think, that it did not begin with the Big Bang, starts to look less like a Maverick's fantasy and more like a possibility worth taking seriously. So let us take it seriously. Let us set aside the statistical debates about faint circles in microwave maps and ask the more direct question: can conformal cyclic cosmology actually explain what Webb is seeing? Can it solve the puzzle of the early galaxies, the impossible black holes, the premature chemistry? Does the model work when you apply it to the specific problems that are currently breaking the standard timeline? The answer, according to Penrose and a small but growing number of researchers willing to engage with CCC on its own terms, is yes. Not just yes in a vague, hand-waving way, but yes in a concrete, mechanistic way that addresses each puzzle individually and shows how the cyclic framework removes the contradictions that plague lambda CDM. The key is understanding what actually carries over from one aeon to the next. Not matter, not particles, not stars or planets or any physical object. What survives the conformal crossover is information, structure, geometry, the seeds of what will become the next universe's large-scale architecture. Start with the supermassive black holes. In the standard model, these objects are a nightmare. Webb found black holes weighing hundreds of millions, possibly billions of solar masses, sitting in galaxies that existed less than 500 million years after the Big Bang. Growing a black hole that massive from a stellar seed in that amount of time requires either sustained super-Eddington accretion, which is rare and poorly understood, or direct collapse, which requires very specific and unlikely conditions. Either way, you are pushing the physics to its limits and hoping the numbers work out. They barely do, and the more black holes Webb finds, the tighter the squeeze becomes. CCC sidesteps the entire problem by allowing the black holes to start big. In the previous aeon, galaxies formed, evolved, and eventually died. Their central supermassive black holes, the ones that had grown over billions of years through normal processes, remained. As the aeon aged and stars burned out and galaxies drifted apart, these black holes were left behind, drifting through an ever emptier, ever colder universe. Over trillions of years they fed on the occasional stray gas cloud or collided with each other, merging into even larger monsters. Eventually, Hawking radiation took over. The black holes began to evaporate. Slowly at first, then faster as they lost mass. The smallest ones evaporated completely. The largest ones, the ones weighing billions or tens of billions of solar masses, took longer, much longer. By the time the aeon reached its final stages, approaching the conformal crossover, these supermassive black holes were still there, still massive, still radiating. Now here is the strange part. At the conformal boundary, mass becomes ambiguous. In a universe filled only with massless particles, photons and gravitons, there is no way to define an absolute scale. Distances are meaningless because there is nothing to measure them against. Time is ambiguous because massless particles do not experience proper time. The geometry of space-time at the end of one aeon and the geometry at the beginning of the next are conformally equivalent. They are related by a transformation that preserves angles and light paths, but not lengths or durations. A black hole at the end of the previous aeon, just before it fully evaporates, exists in a region of spacetime where the concept of mass is starting to break down. The geometry around it, the curvature, the gravitational field, all of that information is still there. But the mass itself, the thing we usually think of as the source of that geometry, is becoming ill-defined. When the conformal crossover occurs, that geometry carries over into the next aeon. It does not carry over as a black hole because black holes are objects with mass and event horizons, and those concepts only make sense in a universe with a well-defined scale. It carries over as a seed, a region of spacetime with excess curvature, a gravitational potential well that is deeper than the surrounding space. As the next aeon begins and particles acquire mass again, that seed becomes a gravitational attractor. Matter falls into it. It grows. And because it started with a head start, because it inherited the gravitational imprint of a billion solar mass black hole from the previous aeon, it can reach a billion solar masses in the new aeon much faster than if it had started from scratch. This is not magic. It is geometry. The conformal structure of spacetime allows information about the distribution of curvature to survive the transition between aeons, even when the matter and energy that created that curvature have long since decayed or dispersed. The result is that the current aeon does not start from a perfectly smooth, uniform state. It starts with built-in structure, inherited from the previous cycle. The supermassive black holes Webb is finding are not objects that formed in the first few 100 million years of our universe. They are objects that have been growing in one form or another for far longer. Their seeds are older than the Big Bang. The same logic applies to the galaxies. In the standard model, galaxies form slowly. Dark matter collapses into halos. Gas falls into those halos and cools. Stars form. Feedback from those stars heats the gas and slows further star formation. The process is self-regulating, which is why it takes so long. You cannot just dump all the gas into stars at once because the radiation pressure and supernova explosions blow the gas away. Galaxy formation is a stuttering, inefficient process that requires billions of years to build up significant stellar mass. Webb is finding galaxies with billions of solar masses in stars at redshifts of 10, 12, even higher. Less than 500 million years after the Big Bang, the timeline does not work, unless the galaxies did not start from scratch. In CCC, the large-scale structure of the previous aeon, the distribution of matter and dark matter does not completely disappear at the crossover. The matter itself, yes. The atoms, the stars, the gas, all of that decays or disperses over the trillions of years leading up to the crossover. But the pattern, the clustering, the overdense and underdense regions, that information is encoded in the geometry of spacetime. When the next aeon begins, that pattern re-emerges as density perturbations, regions where the matter density is slightly higher than average. Those overdense regions collapse faster. They form stars faster. They build galaxies faster. The process is not starting from a perfectly smooth initial state. It is starting from a state that already has structure, inherited from the previous cycle. Vera Balasubramanian, a theoretical physicist who has worked on extensions of CCC, has described this as pre-existing density perturbations seeding the next aeon. The galaxies Webb is seeing are not anomalies. They are exactly what you would expect if the initial conditions of the universe were not random quantum fluctuations stretched by inflation, but were instead the residual imprint of structure from a previous cycle. The galaxies had a head start. They did not have to wait for tiny quantum fluctuations to grow into massive overdensities over hundreds of millions of years. The overdensities were already there, baked into the geometry of the conformal crossover. The galaxies just had to light up. This also explains why some of the early galaxies Webb is finding look so mature. They have disks, they have spiral arms, they have old stars. In the Standard Model, these features should take billions of years to develop because they require a galaxy to settle down, to stop merging with other galaxies, to establish a stable rotating structure. But if the galaxies inherited their initial structure from a previous aeon, if they formed in regions where the density perturbations were already organized in specific ways, then they could develop mature features much faster. The structure was already there in potential. It just needed matter to fall into it and light it up. The heavy element problem is even more straightforward. In the Standard Model, the early universe is metal poor, hydrogen and helium only, with trace amounts of lithium. Every heavier element has to be synthesized inside stars and then dispersed by supernova explosions. That process takes time. You need a first generation of stars to form, live and die. Then a second generation forms from the enriched gas, continues the process and dies. Each cycle adds more metals. By the time you get to galaxies like ours, the gas has been through multiple generations of enrichment and contains a few percent metals by mass, detecting significant amounts of oxygen, carbon, nitrogen, and even dust in galaxies less than 500 million years after the Big Bang implies that multiple cycles of star formation and enrichment have already occurred. The timeline is impossibly tight. CCC dissolves the problem by allowing the metals to come from the previous aeon. In the late stages of that aeon, stars had been forming, living and dying for trillions of years. The interstellar medium was heavily enriched with metals. Oxygen, carbon, iron, all the heavy elements were abundant. When the aeon ended and the conformal crossover occurred, the atoms themselves did not survive. Atoms are structures made of massive particles, and mass becomes ambiguous at the crossover. But the information about the chemical composition, the ratios of different elements, the distribution of metals in the gas, that information can survive in a different form. It can survive as patterns in the radiation field, as variations in the energy density, as perturbations that carry through the crossover and re-emerge as the initial chemical state of the next aeon. Penrose has been careful to distinguish between mass and information in his discussions of CCC. Mass, he argues, dies at the conformal boundary. Massive particles cannot exist in a scale-free, conformally invariant geometry. They require a metric, a way to measure distances and define rest frames. At the end of an aeon, when the universe has expanded to the point where only massless radiation remains, massive particles are gone. But information does not require mass. Information can be encoded in correlations, in patterns, in the structure of fields. A photon carries information about where it came from, what emitted it, what wavelength it had. That information travels with the photon, even as the photon's wavelength is stretched by the expansion of space. At the conformal crossover, the patterns in the radiation field, the correlations between different regions, the distributions of energy, all of that carries through. And when the next aeon begins and particles acquire mass again, those patterns become the initial conditions for the new universe, including the chemical composition. This is speculative. Penrose acknowledges that the details of how information transfers across the conformal boundary are not fully worked out. Quantum mechanics, which governs the behavior of particles and fields at small scales, has to be integrated with general relativity, which governs the large-scale geometry of spacetime. Nobody has a complete theory of quantum gravity. CCC makes assumptions about how that integration works, assumptions that are consistent with known physics but not yet proven. But the framework is there, and it makes a clear prediction. If CCC is correct, the early universe should not be chemically pristine. It should show evidence of metal enrichment, inherited from the previous aeon. Webb is finding that evidence. The concept of inherited structure also applies to dark matter. Dark matter is the invisible scaffolding that holds galaxies together. It does not emit light. It does not interact with ordinary matter except through gravity. We know it exists because galaxies rotate too fast to be held together by the gravity of their visible matter alone. There has to be additional mass, a dark halo surrounding each galaxy, providing the extra gravitational pull. In the Standard Model, dark matter halos form first, before galaxies. Ordinary matter falls into those halos and forms stars. The process is slow because dark matter is cold, meaning it moves slowly and clumps together gradually under its own gravity. In CCC, the dark matter halos from the previous aeon can leave imprints on the next. Dark matter particles, if they are massive, would decay or disperse over the trillions of years leading up to the conformal crossover. But the distribution of dark matter, the pattern of halos and filaments and voids, would be encoded in the geometry of spacetime. When the next aeon begins, that pattern re-emerges as the initial distribution of dark matter in the new universe. The halos do not have to form from scratch. They are already there, inherited from the previous cycle. Galaxies can form faster because the gravitational wells are already in place, waiting to be filled. This is a radical rethinking of initial conditions. In the Standard Model, the initial conditions of the universe are set by quantum fluctuations during the inflationary period. Inflation smooths out the universe on large scales, but leaves tiny random variations on small scales. Those variations are the seeds of structure. They grow over time under the influence of gravity, eventually becoming galaxies and clusters. The randomness is essential. It explains why the universe looks statistically uniform on large scales but lumpy on small scales. It explains the pattern of hot and cold spots in the CMB. It explains the distribution of galaxies. CCC offers a different explanation. The initial conditions are not random. They are inherited. The smoothness on large scales is not the result of a brief period of exponential expansion smoothing out earlier irregularities. It is the result of the previous aeon expanding and cooling and emptying out over trillions of years until it reached a state of near-perfect uniformity. The lumpiness on small scales is not the result of quantum fluctuations. It is the residual imprint of the structure that existed in the previous aeon, carried forward through the conformal crossover. The CMB pattern, the galaxy distribution, the clustering of dark matter, all of it is not random. It is a fossil record of the previous universe. If that is true, then the concept of a beginning, the idea that the universe started from nothing 13.8 billion years ago, is misguided. There was no beginning. There was a transition, an event, a moment when the far future of one aeon became the Big Bang of the next. Time did not start. It continued in a new form, with a new scale, but continuous in its geometry and structure. The Big Bang is not the origin of time. It is a phase transition, a reset, a moment when the universe, having reached the end of one cycle, seamlessly entered the next. This reframing changes everything about how we think about cosmology. In the Standard Model, the early universe is special. It is the moment of creation, the origin of all matter and energy, the point from which everything else flows. The laws of physics, the constants of nature, the initial conditions, all of it is set at the Big Bang. Why those particular laws? Why those particular constants? Why those particular initial conditions? The Standard Model has no answer, they just are. Fine-tuned, apparently, to allow for the existence of stars and planets and life, but with no explanation for why the tuning is what it is. CCC offers a different perspective. The constants are not arbitrary. They are the result of a long evolutionary process, refined over countless aeons. The initial conditions are not random. They are inherited from the previous cycle. The universe we see is not the first draft. It is the latest in an infinite series, each one building on the structure of the last, each one carrying forward the information and geometry of its predecessor. The fine-tuning is not a mystery. It is the cumulative result of an eternal process that has had infinite time to explore different configurations and settle into a stable pattern. Penrose has suggested that this might explain why the universe is so well suited for complexity. Stars, planets, chemistry, life, all of these require very specific conditions. The constants of nature have to fall within narrow ranges. The density of matter has to be just right. Too high and the universe collapses back on itself before stars can form. Too low and matter never clumps together at all. The Standard Model treats this as a lucky accident, or invokes the anthropic principle, the idea that we observe a universe capable of supporting life, because if it were not capable of supporting life, we would not be here to observe it. That is true but unsatisfying. It does not explain anything. It just restates the observation. CCC offers a mechanism. If the universe cycles, and if each cycle inherits structure from the previous one, then the cycles that produce conditions favorable for complexity will tend to persist, not because of some guiding intelligence or purpose, but because complexity, once it emerges, leaves imprints that carry forward. Stars enrich the interstellar medium with heavy elements. Those elements survive in some form across the conformal boundary and seed the next aeon. Galaxies organize matter into dense halos. Those halos leave gravitational imprints that shape the structure of the next cycle. Over infinite time, the universe evolves towards states that support the emergence of structure and complexity, not because those states are special, but because they are self-reinforcing. They create the conditions for their own continuation. This is not a proof, it is a hypothesis. But it is a hypothesis that makes testable predictions, and those predictions are currently being tested by Webb and by future missions that will probe even deeper into the early universe. If the galaxies keep getting more massive, more mature, more chemically enriched at higher and higher redshifts, if the black holes keep getting bigger and more numerous, if the timeline keeps getting tighter and the Standard Model keeps stretching to accommodate the observations, then the case for inherited structure, for a cyclic universe, for CCC, grows stronger. Not because Penrose found circles in the CMB, though that would help, but because the overall pattern of observations points toward a universe that is older, in some sense, than the Big Bang. And there is another angle to this. Penrose has argued that CCC resolves the singularity problem. In the Standard Model, the Big Bang is a singularity, a point where the density and temperature of the universe become infinite, and the laws of physics break down. General relativity predicts this singularity, and most physicists assume that quantum gravity, whatever form it takes, will smooth it out. But we do not have a theory of quantum gravity, so the singularity remains a placeholder for our ignorance. In CCC, there is no singularity. The conformal crossover is not a point of infinite density. It is a smooth transition from one geometry to another. The far future of the previous aeon and the Big Bang of the next aeon are the same event viewed from different perspectives. No breakdown, no infinities, just a continuous evolution of space-time. That smoothness is appealing. Singularities are ugly. They are places where the math stops working, where predictions become meaningless. Physicists tolerate them in black holes because they are hidden behind event horizons, cut off from the rest of the universe. But a singularity at the beginning of time, visible to everyone, is harder to accept. CCC removes it. The price is accepting that the universe is eternal, that it has no beginning, that time stretches infinitely backward and forward. For some, that price is too high. For others, it is a relief. An eternal universe is, in a sense, simpler than one that sprang into existence from nothing for no reason. The mechanisms CCC proposes, the inheritance of structure, the transfer of information across the conformal boundary, the seeding of the next aeon by the remnants of the previous one, these are not just philosophical musings, they have concrete implications for what we should observe. And what Webb is observing, the massive early galaxies, the oversized black holes, the premature chemical enrichment, all of it fits more naturally into a framework where the universe had a head start, where the current cycle did not begin from scratch but inherited the groundwork laid by trillions of years of evolution in the previous aeon. The timeline expands, the contradictions ease. The impossibilities become merely improbable, and improbable things happen all the time in an infinite universe. That is the power of CCC as an explanatory framework. It does not just solve one problem, it solves multiple problems at once by changing the assumptions about what the universe is and where it came from. The standard model assumes a beginning. CCC assumes continuity. The standard model treats the Big Bang as the origin. CCC treats it as a transition. The implications ripple outward through every corner of cosmology, changing how we interpret the data, how we build our models, how we think about time itself. Whether the model is correct is still an open question. But it is a question worth asking because the universe Webb is revealing does not look like the universe we expected to see, and when observations do not match predictions, it is time to reconsider the assumptions. Time, perhaps, to imagine that the beginning was never a beginning at all, just the latest turn in a cycle that has been running forever and will keep running long after the last star in our aeon burns out and the universe fades into the cold, empty, massless state that will become the Big Bang of whatever comes next. That smoothness is appealing. Singularities are ugly. They are places where the math stops working, where predictions become meaningless. Physicists tolerate them in black holes because they are hidden behind event horizons, cut off from the rest of the universe. But a singularity at the beginning of time, visible to everyone, is harder to accept. CCC removes it. The price is accepting that the universe is eternal, that it has no beginning, that time stretches infinitely backward and forward. For some, that price is too high. For others, it is a relief. An eternal universe is, in a sense, simpler than one that sprang into existence from nothing for no reason. And if we are going to take that price seriously, if we are going to accept that the universe does not begin but cycles, then we need to understand what that cycle actually looks like. Not just the beginning, the Big Bang crossover that inherits structure from the previous aeon, but the ending, the far future, the long, slow, cold march toward the state where everything we recognize as matter and energy and structure dissolves into something so simple, so empty, so stripped down to its geometric essence that it becomes indistinguishable from the hot, dense beginning of the next cycle. We need to understand how an ending can also be a beginning, how death can be birth, how the universe manages to reset itself without ever actually stopping. So let us go there. Let us follow the thread forward, not backward. Let us trace the future of our universe, the current aeon, all the way to its conclusion. Let us watch as the stars burn out, the galaxies drift apart, the black holes evaporate, and the entire cosmos fades into a cold, dark, nearly empty void. And then let us watch as that void, through the strange logic of conformal geometry, transforms seamlessly into the next Big Bang. Because that is what CCC predicts, that is the mechanism, that is the engine that keeps the cycle running. The ending is not an ending, it is a transition. And understanding that transition is the key to understanding whether the universe truly has no beginning. In standard cosmology, the far future is bleak. The universe is expanding, and not just expanding, the expansion is accelerating. This was one of the most surprising discoveries in late 20th century physics. In the 1990s, two independent teams studying distant Type 1a supernovae, exploding stars that serve as cosmic distance markers, found that the most distant supernovae were dimmer than expected. That dimness implied they were farther away than they should have been if the universe were expanding at a constant rate. The only explanation was that the expansion was speeding up. Something was pushing the galaxies apart faster and faster over time. Physicists call that something dark energy, and it makes up about 70% of the total energy content of the universe. We do not know what it is. We do not know why it exists. We just know it is there, driving the acceleration. Because of dark energy, galaxies that are not gravitationally bound to each other are moving apart. The farther away they are, the faster they recede. Eventually, billions of years from now, galaxies outside our local group, the cluster of galaxies that includes the Milky Way and Andromeda and a few dozen smaller galaxies, will drift so far away that their light will no longer reach us. They will cross what is called the cosmic event horizon. Not because they are falling into a black hole, but because the space between us and them is expanding faster than light can travel across it. From our perspective, they will vanish, and from their perspective, we will vanish. The observable universe will shrink, not because anything is moving closer, but because the things that were once visible are being carried beyond the boundary of what light can ever reach. Meanwhile, inside our local group, stars will keep forming for a while. Gas clouds will collapse, ignite, burn through their fuel, and die. The massive stars will explode as supernovae. The medium and small stars will swell into red giants, shed their outer layers, and collapse into white dwarfs. The smallest stars, the red dwarfs, will burn slowly and steadily for trillions of years. Eventually, though, the gas will run out. The raw material for new stars, the hydrogen and helium scattered through the interstellar medium, will be used up. Star formation will stop. The universe will enter what astronomers call the degenerate era, a time when the only stars left are the long-lived remnants, white dwarfs, neutron stars, black holes, no new stars, no bright blue giants. No supernovae lighting up the darkness, just the slow cooling of the embers left behind. The degenerate era lasts a long time, tens of trillions of years. During that time, white dwarfs, which are the leftover cores of sun-like stars, will gradually radiate away their heat. They start out hot, glowing faintly in the infrared and visible spectrum. Over time, they cool. After about 10 to the 15 years, a quadrillion years, they will have cooled to the temperature of the cosmic microwave background. After that, they keep cooling, eventually becoming black dwarfs, cold, dark lumps of carbon and oxygen drifting silently through space. None of these objects exist yet. The universe is only 13.8 billion years old, far too young for any white dwarf to have cooled all the way to a black dwarf. But given enough time, they all will. Neutron stars, the remnants of more massive stars, will also cool. They start out incredibly hot, with surface temperatures in the millions of degrees. Over time, they radiate that heat away. Eventually, they too will fade into the background, dark and cold. Black holes, the remnants of the most massive stars, do not cool in the traditional sense. They do not radiate heat like a white dwarf or a neutron star, but they do radiate. Stephen Hawking showed in the 1970s that black holes emit particles, a process now called Hawking radiation. The radiation comes from quantum effects near the event horizon, where particle-antiparticle pairs are constantly forming and annihilating. Occasionally, one particle falls into the black hole and the other escapes. From the outside, it looks like the black hole is emitting radiation. That radiation carries energy away from the black hole, which means the black hole loses mass over time. It evaporates. The rate of evaporation is incredibly slow for large black holes. A black hole with the mass of the Sun would take about 10 to the 67 years to evaporate completely. A supermassive black hole weighing 1 billion solar masses would take about 10 to the 100 years. Those numbers are almost meaningless. They are so large that they dwarf the current age of the universe by factors of trillions of trillions. But in the far future, when enough time has passed, every black hole will evaporate. The small ones first, then the larger ones, until eventually even the supermassive black holes at the centers of galaxies are gone. When they go out with a flash, a final burst of radiation as the last bit of mass converts into energy and the event horizon shrinks to zero. And then nothing. Just empty space where the black hole used to be. By the time the black holes evaporate, the universe will be unrecognizably old, 10 to the 100 years. That is a 1 followed by 100 zeros. For context, the current age of the universe is about 10 to the 10 years. You would need to live through the current lifetime of the universe 10 billion times, and then do that entire process again 90 more times, to reach 10 to the 100 years. It is a span of time so vast that human brains are not equipped to grasp it. And yet, in the context of eternity, it is nothing, a blink. Because after the black holes evaporate, the universe keeps going. At this point, the universe enters what physicists call the photon era. Almost all the matter is gone. The stars have burned out. The white dwarfs and neutron stars have cooled into invisible remnants. The black holes have evaporated. What is left is radiation. Photons, the particles of light. Gravitons, the hypothetical particles of gravity, which have never been directly detected but are predicted to exist by quantum field theory. Neutrinos, which are nearly massless and barely interact with anything. And a thin scattering of leftover particles, electrons, positrons, protons, that have not yet decayed or annihilated. The universe at this stage is cold. The temperature is far below the current cosmic microwave background temperature of 2.7 Kelvin. It might be 10 to the minus 30 Kelvin or lower, so close to absolute zero that the difference is academic. The universe is also enormous. It has been expanding for 10 to the 100 years, maybe longer. The distances between any two objects, if there are still objects, are so vast that they might as well be in separate universes. Nothing interacts with anything else. There are no stars to light the way, no galaxies to provide landmarks, no structure. Just an infinite expanding void filled with faint radiation and the occasional particle drifting alone through the dark. This is the heat death, the end state predicted by thermodynamics. The universe has reached maximum entropy. Every energy gradient has been smoothed out. Every hotspot has cooled. Every massive object has decayed or dispersed. There is no way to extract useful work from the system because there are no differences left to exploit. No hot and cold, no dense and sparse. Just uniform, cold, empty space stretching in all directions forever. This state is what Penrose calls the far future of the aeon. And it is here, in this cold, empty, seemingly dead universe, that something remarkable happens. The universe forgets its scale. To understand what that means, you have to think about what it means for something to have a size. Size is a relative concept. An object is big or small compared to something else. A basketball is large compared to a marble and small compared to a planet. But those comparisons only work if you have multiple objects to compare. If the universe contains only a single object, how big is it? The question does not make sense. There is no reference frame, no ruler, no way to say whether the object is 1 meter across or 1 light year across, because there is nothing else to measure it against. Now take that idea to the extreme. In the far future, the universe is filled with photons and gravitons, massless particles, particles that travel at the speed of light and do not experience time. From the perspective of a photon, it is emitted and absorbed in the same instant. It does not age. It does not have a rest frame. And if the universe contains only massless particles, then there is no way to define a scale. You cannot say the universe is a certain size because there is nothing in it with mass, nothing with a defined length scale, nothing to measure against. Distances still exist in some formal mathematical sense, but they are meaningless. The geometry of the universe at this stage is described entirely by angles and light paths, not by lengths or sizes. This is conformal geometry. A conformal transformation is a mathematical operation that changes distances but preserves angles. If you take a shape and stretch it or shrink it uniformly in all directions, the angles between its lines stay the same even though the lengths change. A square stretched into a larger square still has 90-degree corners. A circle stretched into a larger circle is still a circle. In a universe filled only with massless particles, the geometry is conformally invariant. The equations describing the behavior of those particles do not change if you rescale all the distances by some constant factor. You can multiply every distance by 1,000,000 or divide it by 1,000,000,000, and the physics looks exactly the same. Penrose realized that the far future of one aeon, a cold, empty universe dominated by massless particles, is conformally equivalent to the Big Bang of the next aeon. The Big Bang is also a state dominated by massless particles. In the first moments after the Big Bang, the universe was so hot that particles could not form stable structures. Protons and electrons existed, but they were moving so fast, smashing into each other with so much energy that they could not bind together into atoms. The universe was a plasma of free particles and radiation, and in that plasma, before the universe cooled enough for atoms to form, the dominant players were photons and other massless or nearly massless particles. The geometry of that early plasma is also conformally invariant. So you have two states, the far future of one aeon, the early moments of the next aeon. Both are dominated by massless particles. Both have conformally invariant geometries. Penrose showed that you can take the equations describing the first state, apply a conformal transformation, and get the equations describing the second state. Mathematically, they are the same. The infinite future of one universe maps onto the Big Bang of the next. There is no singularity, no point where the density or temperature becomes infinite, no breakdown of the laws of physics, just a smooth transition from one geometry to another. This is the heart of conformal cyclic cosmology. The ending of one aeon is the beginning of the next, not in a vague metaphorical sense, but in a precise mathematical sense. The transition is not a violent event. It is not an explosion. It is a smooth geometric transformation, a crossover where the far future of the old universe, stretched to unimaginable scales, becomes the hot, dense beginning of the new universe, compressed to subatomic scales. The conformal equivalence means there is no boundary between them, no moment where one ends and the other begins, just a continuous evolution of space-time, cycling from expansion to contraction, from hot to cold, from structure to emptiness and back again. Let us walk through the transition step by step. Start with the far future. The universe is old, 10 to the 100 years, maybe 10 to the 120 years. The black holes have evaporated. The last burst of Hawking radiation from the last supermassive black hole faded trillions of years ago. What remains is a thin gas of photons, gravitons, and a few leftover particles. The temperature is essentially zero. The expansion is continuing, driven by dark energy or whatever the equivalent of dark energy is in this late stage. Distances between any two particles are growing exponentially. The universe is approaching a state of infinite dilution, infinite emptiness. At this point, the concept of mass has become ambiguous. The particles that remain, the photons and gravitons, have no rest mass. The occasional electron or proton that has somehow avoided annihilation for 10 to the 100 years is so isolated, so far from anything else, that its mass is effectively irrelevant. It is not interacting with anything. It is not exerting any gravitational influence on anything nearby because there is nothing nearby. In a practical sense, it might as well be massless. The universe as a whole has no defined scale. If you were somehow able to observe it, which you could not because you would not exist, you would not be able to say how big it was. There would be no rulers, no clocks, no landmarks, just geometry. Angles and light paths stretching in all directions. Now apply a conformal transformation. Take every distance in the universe and divide it by some enormous number. A number so large that the vast, empty, infinitely dilute universe compresses down to a tiny, dense region. The photons, which were spread across unimaginable distances, are now packed together. The gravitons are squeezed into a small volume. The geometry has been rescaled, but the angles, the relationships between light paths, the fundamental structure are preserved. And because the universe was conformally invariant, because it had no defined scale to begin with, this rescaling does not change the physics. The equations describing the photons and gravitons before the transformation are the same as the equations after the transformation. Nothing has been broken, nothing has been violated. The universe has just been re-expressed in a different scale. What you have now is a hot, dense state, a state where particles are packed together, where the temperature is high, where energy density is enormous. This is the Big Bang. But it is not a singularity. It is not a point of infinite density. It is just the far future of the previous aeon, viewed through a different lens, rescaled to a new frame of reference. The transition is smooth. The geometry is continuous. The conformal transformation is the mathematical operation that connects the end of one cycle to the beginning of the next. There is no moment of creation, no point where time starts, just a crossover, a change of scale, a reset. Penrose has described this as a join, the far future of one aeon and the Big Bang of the next are joined together conformally. If you were somehow able to travel along a light path from the previous aeon into the next, you would not notice a boundary. You would not pass through some dramatic threshold. The geometry would just shift, smoothly and continuously, from one scale to another. Time, from the perspective of a massless particle, is ambiguous. A photon does not experience duration. For a photon, the journey from emission to absorption is instantaneous, even if the journey takes billions of years from the perspective of an observer with mass. At the conformal boundary, where the universe is composed entirely of massless particles, time itself becomes ill-defined. The infinite future of one aeon and the singular beginning of the next are, in a sense, the same instant. This is difficult to visualize. Our brains are wired to think of time as a linear sequence, one moment following another, with clear distinctions between past, present, and future. But at the conformal boundary, those distinctions break down. The far future, stretched to infinity, and the Big Bang, compressed to a point, are conformally equivalent. They are the same event, described in different coordinates. The universe does not end and then begin again. It transitions, it cycles, it resets its scale and continues. The role of black hole evaporation in this process is critical. Black holes are the last massive objects to survive. They accumulate matter throughout the aeon, growing in mass as galaxies collide and stars fall in. By the late stages of the aeon, the supermassive black holes at the centers of galaxy clusters are the dominant gravitational structures. Everything else has dispersed or cooled into invisibility. Those black holes sit there for trillions upon trillions of years, slowly losing mass through Hawking radiation. The radiation they emit is composed of photons and other particles, mostly massless or nearly massless. As the black hole evaporates, it is converting its mass into radiation, transferring the last reservoir of energy locked in massive objects into the massless radiation field that will dominate the far future. When the black hole finally evaporates completely, the last of the mass is gone. The universe has been purged of massive particles. What remains is pure radiation, pure geometry. And because the radiation is massless, the universe becomes conformally invariant. The black holes, in a sense, are the last obstacles preventing the conformal crossover. Once they are gone, the transition can occur. The far future state is complete. The universe has reached the configuration where it can smoothly join onto the next aeon. This also explains why the next aeon can contain structure so quickly. In the standard model, the early universe is supposed to be smooth and featureless, with only tiny quantum fluctuations to seed the formation of galaxies billions of years later. But if the early universe is actually the far future of the previous aeon, rescaled and reset, then it inherits structure from that previous cycle. The positions of the black holes before they evaporated, the distribution of radiation they emitted, the patterns in the gravitational field, all of that information survives the conformal transformation. It does not survive as matter. The matter is gone. But it survives as patterns in the geometry, as variations in the energy density, as imprints that carry forward and become the initial conditions of the next aeon. The galaxies Webb is finding, the massive black holes, the advanced chemistry, all of it makes sense in this framework. The next aeon did not start from scratch. It started with a blueprint, a template inherited from the previous cycle. The black holes that evaporated at the end of the last aeon left gravitational imprints that became the seeds of the supermassive black holes in the next. The stars that enriched the interstellar medium with metals left chemical signatures that carried through the crossover as patterns in the radiation field, re-emerging as the initial metallicity of the new universe. The galaxies that formed and evolved over trillions of years left structural imprints that became the density perturbations driving galaxy formation in the next cycle. Nothing was created from nothing. Everything was inherited, recycled, transformed. The philosophical implications are staggering. If CCC is correct, then the universe has no beginning. Time does not start. It has always been running. The Big Bang is not the origin of everything. It is just a moment, a transition, one beat in an infinite rhythm. Before our universe there was another, and before that another. The chain extends backward forever. There is no first aeon, no prime mover, no initial cause, just an eternal process, cycling endlessly, each aeon building on the last, each crossover carrying forward the structure and information accumulated over trillions of years. This removes the need for a creator. It removes the need for fine-tuned initial conditions. It removes the singularity problem, the entropy problem, the question of why the universe exists at all. The universe exists because it always has. It did not come from nothing. It came from the previous aeon, which came from the one before that, stretching back infinitely. The laws of physics, the constants of nature, the conditions that allow for stars and planets and life, are not arbitrary. They are the result of an evolutionary process that has had infinite time to refine itself. The universe is not a one-time creation. It is an ongoing process, an eternal cycle of death and rebirth, expansion and contraction, forgetting and remembering. For some, this is liberating. The idea of an eternal universe, a cosmos that has no need for an external cause, aligns with a naturalistic worldview. The universe is self-sufficient. It does not require a beginning because it never began. It simply is, cycling through its phases, endlessly creating and destroying structure, endlessly transforming energy and matter and geometry into new configurations. The heat death is not an ending. It is a preparation. The universe is not dying. It is resetting, preparing for the next cycle, the next Big Bang. The next 13.8 billion years, or 26.7 billion years, or however long the current aeon actually lasts, of stars and galaxies and planets and life, and then another heat death, and another reset, forever. For others, this is unsettling. An eternal universe with no beginning feels incomplete. It raises the question of why the cycle exists at all. If there is no first cause, no starting point, then what sustains the process? Why does the universe cycle rather than simply ending? The answer CCC offers is that the process sustains itself. The conformal geometry, the mathematical structure that allows the far future of one aeon to map onto the Big Bang of the next, is built into the fabric of space-time. It is not imposed from outside. It is a consequence of how general relativity and the behavior of massless particles interact at extreme scales. The universe cycles because that is what the equations allow. That is the natural evolution of a cosmos governed by those laws. Whether that answer is satisfying depends on your philosophical commitments, but it is an answer, and it is an answer that makes testable predictions. CCC predicts that the early universe should show evidence of inherited structure. It predicts massive galaxies and black holes at high redshifts. It predicts chemical enrichment earlier than the Standard Model allows. It predicts Hawking points in the CMB. Some of those predictions are controversial. Some have been tested and remain ambiguous, but the framework is there, and it is being refined as new data comes in. The universe Webb is revealing is forcing cosmologists to reconsider assumptions that have been in place for decades. The timeline is too tight, the structures are too mature, the chemistry is too advanced. Something about the standard story is not adding up. CCC offers an alternative, not a fringe theory from the margins of science, but a serious model developed by a Nobel Prize-winning physicist, grounded in general relativity, making specific predictions that can be tested. Whether it is correct remains to be seen. But the fact that it is being discussed, debated, tested, is a sign that the field is open to the possibility that we have misunderstood something fundamental. The end of our universe, whenever it comes, will not be the end. It will be a transformation, a moment when the geometry of space-time shifts, when the scale resets, when the cold, empty void of the far future becomes the hot, dense plasma of the next Big Bang. The stars will burn out, the galaxies will drift apart, the black holes will evaporate. And from that emptiness, that forgetting of scale, a new universe will emerge, not created, not born from nothing, but continuing, recycling, carrying forward the information and structure of everything that came before. An eternal engine, a cosmos that never stops. A cycle with no beginning and no end, running forever through an infinity of aeons, each one leaving its mark on the next, each one a chapter in a story that was never written because it was never begun. It simply is, it always has been, and it always will be. The universe cycles because that is what the equations allow. That is the natural evolution of a cosmos governed by those laws. Whether that answer is satisfying depends on your philosophical commitments, but it is an answer, and it is an answer that makes testable predictions. CCC predicts that the early universe should show evidence of inherited structure. It predicts massive galaxies and black holes at high redshifts. It predicts chemical enrichment earlier than the Standard Model allows. It predicts Hawking points in the CMB. Some of those predictions are controversial, some have been tested and remain ambiguous. But the framework is there, and it is being refined as new data comes in. And now here we are, at the end of this story, or what feels like the end. Except if Penrose is right, there are no ends, just transitions. Crossovers, moments where the scale resets and the process continues. So maybe this is not an ending at all, maybe it is just a pause. A chance to look back at what we have learned, what the James Webb Space Telescope has shown us, and ask the question that has been sitting quietly underneath every observation, every spectrum, every impossibly early galaxy. Have we been wrong about when the universe began? Let us lay it out cleanly. No ambiguity, no hedging. Here is what Webb found. Galaxies at redshifts of 10, 12, 13 and higher. Galaxies that existed when the universe was only 300 to 500 million years old. Galaxies that were not small, dim, chaotic proto-galaxies struggling to light their first stars. They were massive, structured. Some of them had disks, some had spiral arms. Some showed clear signs of organized star formation, regions lit up with young blue stars, surrounded by older red populations. These were not infants, they were teenagers at minimum, possibly adults, fully formed systems sitting in a universe that was supposed to be a nursery. Sitting inside some of those galaxies were black holes, not stellar mass black holes, the kind you get when a massive star collapses. Supermassive black holes, objects weighing hundreds of millions, possibly billions of times the mass of our sun. Black holes that should take 1 billion years to grow from a stellar seed, even if they feed continuously at the absolute maximum rate allowed by physics. And they were there, shining brightly as quasars, less than 500 million years after the Big Bang. The timeline does not work. You cannot fit that much growth into that little time without breaking the rules. And then there was the chemistry. Oxygen, carbon, nitrogen, dust, heavy elements that should not exist in significant quantities until stars have lived, died, and exploded, scattering their guts into the interstellar medium. That process takes time, multiple generations of stars, hundreds of millions of years at minimum. More realistically, closer to 1 billion. Webb found oxygen emission lines in galaxies at redshift 13.2, galaxies that were only 325 million years old, nitrogen in galaxies at redshift 10.6, dust in galaxies at redshift 11. Every detection is a flag planted in a timeline that should not support it. Every spectrum is a quiet challenge to the story we have been telling for nearly a century. The standard model, lambda CDM, the framework that has guided cosmology since the 1980s, predicted none of this. It predicted small galaxies forming slowly. It predicted stellar mass black holes growing patiently over billions of years. It predicted a chemically pristine early universe, gradually enriched by successive generations of stars. What Webb found was the opposite: big galaxies forming fast, massive black holes appearing early, chemistry showing up centuries too soon. The observations do not match the predictions. That is not a minor discrepancy. That is a crisis. To be fair, not everyone agrees it is a crisis. Rachel Somerville, an astrophysicist at the Flatiron Institute, has argued that the standard model is resilient enough to accommodate these observations. She thinks we need to rethink galaxy formation, adjust our assumptions about how efficiently stars form in the early universe, refine our models of black hole growth, tweaks, not overhauls. She has said publicly that she thinks it is more likely we can fit the Webb data within the existing paradigm than that we need to abandon lambda CDM entirely, and she is not alone. A significant portion of the cosmology community is still betting on the standard model. They have seen anomalies before. They have seen data that looked incompatible with the framework, only to be explained later by better modeling or more careful analysis. They are skeptical of claims that the universe is broken. They are waiting for more data, more simulations, more time to see if the tension resolves. But there is another group, smaller but growing, that thinks the tension is real, that the observations are not going to go away with better models, that something fundamental about the timeline is wrong. This group points to the Hubble tension, the disagreement over the expansion rate of the universe, which has persisted for more than a decade despite increasingly precise measurements. They point to the sheer number of early galaxies Webb is finding, far more than the standard model predicted. They point to the black holes that should not exist yet. They point to the chemistry that appeared too soon. And they say quietly at first, but with increasing confidence, that maybe lambda CDM is not just incomplete. Maybe it is wrong. Not about everything. It still explains the cosmic microwave background beautifully. It still matches the large-scale structure of the universe. But maybe it is wrong about the beginning. Maybe 13.8 billion years is not the whole story. Enter Conformal Cyclic Cosmology. Penrose's model does not just tweak the standard framework. It replaces the foundation. It says the Big Bang was not a beginning, it was a transition, a crossover from the far future of the previous aeon into the hot, dense start of the next. The universe is not 13.8 billion years old. It is older, far older. Not in the sense that the current aeon has been running longer than we thought, but in the sense that the current aeon inherited structure, mass, chemistry from a previous cycle that ran for trillions of years before the crossover occurred. The galaxies Webb is finding are not anomalies. They are exactly what you would expect if the early universe started with a blueprint, a template, carried forward from the previous aeon. The black holes did not have to grow from stellar seeds in a few 100 million years. They inherited gravitational imprints from black holes that existed in the previous cycle and evaporated at the conformal boundary, leaving seeds that could grow rapidly once matter started falling in. The chemistry did not have to be synthesized from scratch. It was inherited, encoded in the patterns of radiation that survived the crossover and re-emerged as the initial metallicity of the new universe. CCC solves the problems Webb is creating for the Standard Model. It explains the early galaxies, it explains the massive black holes, it explains the advanced chemistry. It does all of this without invoking new physics, without adding exotic particles or forces, just by changing the assumptions about what the Big Bang was and where it came from. The price is accepting that the universe is eternal. That time has no beginning. That what we call the Big Bang is just one beat in an infinite rhythm of expansion and contraction, death and rebirth, forgetting and remembering. For Penrose, that price is worth paying. For many of his peers, it is not. The resistance to CCC is not just about the data. It is about the implications. An eternal universe is philosophically uncomfortable. It removes the singularity, the moment of creation, the origin point. It replaces it with an infinite regress, a cycle that has always been running and always will be. Some scientists find that elegant, others find it unsatisfying. A beginning, even a mysterious one, feels more comprehensible than a process that extends infinitely backward with no starting point. But comprehensibility is not the same as truth. The debate over CCC is ongoing. The model has been tested in multiple ways, and the results are mixed. The Hawking points, the concentric circles in the cosmic microwave background that Penrose claimed were evidence of black hole evaporations from the previous aeon, have not been confirmed by independent analysis. The Planck satellite, with better data and higher resolution, did not find them. That is a serious blow. It does not disprove CCC, but it removes one of the most direct observational supports. Penrose has continued to refine his search methods, applying different statistical tests, looking at different angular scales, but the circles remain elusive. Most cosmologists who have examined the claim conclude that the patterns Penrose identified are consistent with random noise. They are not signals. They are artifacts of the search process, the kind of false positives that arise when you analyze a complex dataset with sensitive statistical tools and do not apply rigorous controls. But the Hawking points are not the only test of CCC. The model makes broader predictions. It predicts that the early universe should show more structure, more mass, more chemical enrichment than the Standard Model allows. And that is exactly what Webb is finding. It predicts that black holes should be larger and more numerous at high redshifts. Webb is finding that too. It predicts that the timeline of galaxy formation should be compressed, that things should happen faster than lambda CDM expects. Again, the observations support it. CCC does not need the Hawking points to be vindicated. It needs the overall pattern of observations to keep pointing in the direction of inherited structure of an early universe that was not starting from scratch. And so far, that is where the data is pointing. The question is whether the Standard Model can adapt. Can lambda CDM stretch far enough to accommodate the Webb observations without breaking? Some researchers think yes. They are working on new models of star formation that allow for much higher efficiency in the early universe. They are exploring scenarios where black holes grow through super-Eddington accretion, feeding in short, violent bursts that bypass the normal limits. They are investigating direct collapse black holes, primordial black holes, exotic mechanisms that could produce massive seeds early enough to match what Webb is seeing. These are not small adjustments, they are significant modifications to the framework. But they are modifications, not replacements. The foundation, the idea that the universe began 13.8 billion years ago in a singular Big Bang event, remains intact. Penrose would argue that this is just patchwork, that the Standard Model is being stretched and twisted to fit observations it was never designed to explain, that each new adjustment introduces new problems, new fine-tuning, new complications, that at some point you have to ask whether it makes more sense to keep adding epicycles to a broken model or to step back and consider a fundamentally different framework. CCC is that framework. It is not perfect. It has gaps, particularly around how entropy and information transfer across the conformal boundary, but it is coherent, it is testable, and it makes predictions that are being confirmed by the most powerful telescope humanity has ever built. The next few years will be critical. Webb is going to keep observing. It is going to push deeper into the early universe, finding galaxies at even higher redshifts, probing the era when the first stars ignited, mapping the chemical evolution of the cosmos in unprecedented detail. If the trend continues, if the galaxies keep getting more massive, the black holes keep getting bigger, the chemistry keeps showing up earlier, then the case for inherited structure, for a cyclic universe, for CCC, grows stronger. Not because of faint circles in the CMB, but because the overall pattern of observations cannot be explained by a singular Big Bang with a finite timeline. The universe Webb is revealing is too mature, too developed, too rich in structure to fit comfortably into 13.8 billion years. There are other tests on the horizon. Future missions like LISA, the Laser Interferometer Space Antenna, will detect gravitational waves from supermassive black hole mergers across cosmic time. If CCC is correct, the distribution and timing of those mergers should show patterns that reflect the cyclic nature of the universe. The mergers from late in the previous aeon, the ones that produced the Hawking points, should have left signatures in the gravitational wave background, faint echoes that could be detected with sensitive enough instruments. ALMA, the Atacama Large Millimeter Array, is mapping the distribution of dust and molecules in high redshift galaxies, tracing the chemical evolution of the early universe with exquisite precision. If the dust and molecules show up earlier and in greater abundance than Lambda CDM predicts, that is another point in favor of CCC. Each new observation is a test. Each new dataset is a chance to refine the models, to see which framework fits the data better. But beyond the tests, beyond the data, there is a deeper question. What does it mean if Penrose is right? What does it mean to live in a universe that has no beginning? A cosmos that has been cycling through aeons for an infinite span of time, each one building on the last, each one carrying forward the information and structure of everything that came before. It changes how we think about origins. There is no creation event, no moment when the universe sprang into existence from nothing, no need for a prime mover or an initial cause. The universe exists because it always has. It is self-sustaining, self-perpetuating, an eternal engine running through infinite cycles of expansion and contraction, hot and cold, life and death. It changes how we think about our place in the cosmos. In the Standard Model, we are close to the beginning. Only 13.8 billion years separate us from the origin of everything. The universe is young, we are early. The first civilizations, if they exist, are our contemporaries. The first planets, the first stars capable of supporting life, formed only a few billion years before ours. There is a sense of closeness, of proximity to the start. In CCC, that closeness is an illusion. The current aeon may be 13.8 billion years old, but the cycle has been running forever. There is no first aeon, no first planet, no first civilization. We are not early. We are not close to the beginning. We are somewhere in the middle of an infinite process, one iteration among countless others, inheritors of structure and chemistry and perhaps even patterns of complexity that have been refined over trillions upon trillions of years across uncountable cycles. That is humbling, not in a dismissive way, not in a way that makes us insignificant, but in a way that puts us in perspective. We are part of something vastly larger and older than we imagined. The atoms in our bodies were not forged in the first generation of stars in this aeon. They were recycled from previous cycles, carried forward through conformal crossovers, re-embodied in new stars and planets, and eventually in us. The structure of the Milky Way, the distribution of galaxies in our local cluster, the seeds of the supermassive black hole at the center of our galaxy, all of it inherited from processes that began long before the Big Bang. We are not just children of the stars, we are children of the cycle, products of an eternal process that has been shaping and reshaping the universe for longer than time itself. If time itself can be said to have a duration, and it is beautiful, not in a sentimental way, in a structural way. The idea that the universe does not need a beginning, that it is self-sufficient, that it contains within itself the mechanism for its own continuation, is elegant. It is a closed loop. The far future feeds into the next beginning. The ending is the birth. The death is the renewal. Nothing is wasted. Nothing is lost. Every black hole that evaporates, every star that burns out, every galaxy that fades into the dark, contributes to the conformal crossover that will become the next Big Bang. The universe recycles itself completely. Not just matter and energy, but information, structure, the seeds of complexity. It is an eternal return, but not in a repetitive sense. Each cycle is different. Each aeon builds on the last, inherits its patterns, refines its structures. The universe is not just old, it is experienced. It has been through this process infinite times, and each time it carries forward what it has learned. Whether that is true depends on the data, on whether the observations keep pointing toward inherited structure, on whether the standard model can stretch far enough to accommodate what Webb is seeing, or whether it breaks under the strain, on whether Penrose's predictions, the Hawking points, the advanced chemistry, the massive early galaxies hold up under scrutiny or fade into the noise. The debate is not settled. The question is not answered, but it is being asked, seriously, by serious people, in serious journals. The idea that the universe has no beginning, that 13.8 billion years is not the whole story, that the Big Bang was a transition rather than an origin, has moved from the margins into the conversation. It is not the consensus. It may never be, but it is no longer dismissible. And that is where we are, standing at the edge of a possibility, looking at a universe revealed by the James Webb Space Telescope, a universe that does not quite fit the story we have been telling. Massive galaxies where there should be none, black holes that grew too fast, chemistry that appeared too soon, all of it pointing, not definitively but suggestively, toward a cosmos that is older, stranger, more layered than we thought, toward a timeline that stretches infinitely backward, not as a vague philosophical speculation, but as a concrete, testable model with mechanisms and predictions and mathematics, toward an eternal cycle of death and rebirth, expansion and contraction, forgetting and remembering, running forever through aeons we will never see, leaving imprints we are only now learning to read. Was 13.8 billion years truly the beginning, or was it just the latest pulse of an undying universe? The answer is not in yet. The data is still coming in. Webb is still observing. The models are still being refined. The debate is still unfolding. But the question is real. The tension is real. The cracks in the standard model are real. And if Penrose is right, if the universe truly has no beginning, if time stretches infinitely backward and forward through cycles we are only now beginning to understand, then we are living through a moment of profound realization, not the moment we discovered the universe, but the moment we discovered it has been here, in one form or another, forever, that it will continue, in one form or another, forever. That the beginning we thought we knew was never a beginning at all, just a fading line between one aeon and the next, a crossover, a reset, a breath in an infinite rhythm that was never started because it was never needed to start. It simply is, it always has been, and it always will be. So here we are, at the end of a story that might not have an ending, staring at galaxies that should not exist yet, black holes that grew too fast, chemistry that appeared centuries too soon. Every observation from the James Webb Space Telescope is a quiet challenge to the timeline we built our entire cosmology on. 13.8 billion years. A number so precise, so confident, that questioning it felt almost rude. And yet the universe Webb is revealing does not fit inside that number. It is too developed, too structured, too old. Roger Penrose looked at that tension and proposed something most of his peers considered impossible: that the Big Bang was not a beginning, that time does not start, that what we call the origin of everything was just a transition, a crossover from the far future of a previous aeon into the hot, dense start of ours, an eternal cycle with no first moment, no creation event, no need for a universe to spring from nothing, just geometry, just mathematics, just the quiet, relentless logic of space-time doing what it has always done, forgetting its scale, resetting, continuing. The model is not proven. The circles in the cosmic microwave background remain contested. The mechanisms are not fully worked out, but the observations keep piling up, and they keep pointing in the same direction, toward a universe that had a head start, toward structure inherited from something that came before, toward a beginning that was never a beginning at all. Whether Penrose is right or wrong, the question is now unavoidable. Did the universe begin, or has it simply been running forever, cycling through aeons we will never see, leaving fingerprints we are only now learning to read? The date